GCAM. Then we proceed with Jorge Rueda. That was the next one. Rahim Murad.
Okay, thank you. So the slight change was not only for the replacement of the first speaker, also a bit. First, I will talk about the ultra-relativistic prompt emission phase in GRBs. Then I will present something about this Chinese satellite that we have been working recently inside HXMT. Also, the GCAM. So, in the title, I use the, in the title, I use the term self-similarity. First, I will introduce some historical context that led us to this definition of ultra-relativistic prompt emission phase, and the concept that led again to this concept of the self-similarity, which during the talk I will tell how it is different from this self-similarity and self-organized criticality in mathematics, and how operationally we define it.
Hello?
So just start.
You started?
Yeah, just.
Okay, just a second. Let me say a few words. We are progressing remarkably on all fronts. It's incredible. Thanks also to Roland, who was here and gave few of you present, but he gave a very, very important talk last night, and we are collaborating. Now, we progress stepwise. We completed yesterday the big announcement of the new era, the egg, the chicken, and the solution given by Columbus. Namely, we are in presence for the first time of matter, baryonic, and the dark matter. This is the testimony of the residents. This was yesterday. Now we are progressing to understand better, technically, how to check. And today, we want to be two exceptional talks. The one by Rahim, and the one by Rueda. Now, what is exceptional in these two talks? Exceptional in these two talks, they will be dedicated to gamma ray bursts. It is clear that there are two different gamma ray bursts types. This will be clear tomorrow, not today. But we start the point of departure, which will be the final my lecture on Friday, is the OB supernova, which start the gamma ray burst. But as soon as the gamma ray burst start, and we will do that at the end of the week with the OB supernova, something strange happened. Namely, and this is something related to me personally. A few times in my life I gave a promise to important people. And I did a promise to Werner Heisenberg. After discovering the black hole, he was against astronomy and all these things, and especially against the general relativity. I will tell you another time, but very strongly against. Therefore, we have discovered black holes. I needed to make him aware of this, that was important. And the best way to convince him, I said, look, we will show that the turn on of the black hole is essential to have a ultra-relativistic Euler-Heisenberg process. My personal king to Werner Heisenberg. We continue, and I almost convinced him to inaugurate the meeting of Ravenna. Unfortunately, he died a few days before, could not come. But the promise remained, and today we have enforced this promise. Namely, there is a part of the GRB, what we call the UPE, which does not come from general relativity, but comes from ultra-relativistic Euler-Heisenberg process, the UPE. This is the great message which will be carried on by the first person who understood this in our group, Raim. Why we are so sure that is depending from Heisenberg order? Because it's self-similar. Anything in general relativity cannot be self-similar. You need a linear theory. Electrodynamics, it will give us the evidence for this early phase of a GRB, which is before the birth of the black hole, just a little bit before. That is the field of quantum electrodynamics that the laser people are trying to do. This is the talk, the two talks which will be this morning. They are exceptional. And you will enjoy, after yesterday talk of trying to find fractal, I mean, when you have a fractal, you see it immediately. You have the sub-similarity. This is the talk, the fantastic talk, result of Raim. Please go on. I hope you can use this interruption.
Yes, thank you.
Excuse me, for my ignorance, but can you decipher
Ultra-relativistic prompt emission phase. U is ultra-relativistic
decipher it?
prompt emission, yes, P.
This
So
you will be able to see this. Once you will have the instrument, you will see this similar, this one, that is going to present. It's dramatic. I hope you will see. Okay? And this will be main point for the postman. I have got to use now.
So, thanks again. In this talk, I won't go through the theoretical understanding. It's basically the history, how it led to this concept, also the observational fact that help us to understand more this UP, ultra-relativistic prompt emission phase. So I will be talking about this. Briefly, I mentioned the history, how we have developed the work, how it has been developing. Also, at the end, I will introduce you some new observation by some Chinese satellite that is complementary to Fermi GBM, and I will tell you how it can help us to understand more about prompt emission and the yes, all related to self-similarity. So gamma ray bursts are a transient of prompt gamma ray flashes, for those who don't know. But these transients usually come with later afterglow in X-ray, optical, radio, and sometimes in giga-electron volt, tera-electron volt. And when we talk about prompt emission, is the first, usually first in the taxonomy of the GRBs, the first, when we call about short and long GRB, short GRB usually less than 2 seconds, this prompt emission, and the long around 2 seconds to 100 usually. So UP happens in this area, in this prompt emission, and as you can see, there are many other afterglow and radiation in other energy bands. So GRB is a sequence of episodes, which in this talk I will only talk about the ultra-relativistic prompt emission as I defined, which is high luminous in the Kev-Mev the energy interval, which the characteristic is the thermal component plus a non-thermal continuum, which usually is a band function, phenomenological, or cutoff power law. And also I will introduce why we have been seeking for the self-similarity and what is the difference with the mathematical self-similarity and how we finally go to more mathematical understanding of this part. Okay, this is the story and the history. Let me come here because I cannot see well. This is the story that and history of this idea. First, it started with this extractor energy from the rotational energy of the black hole by Christodoulou and Ruffini. Then the first idea came that if we have the charged black hole, we have charged black hole, Damour and Ruffini proposed that around it we can have this vacuum polarization. And this was the first idea, first theoretical idea that electron-positron pair can be around the black hole in that moment can serve as the energy reservoir for gamma ray burst. So what's this? We have the electric field around the more than the critical Schrödinger value, let's say, it polarized vacuum and create E plus E minus, which is following the theoretical line of Schauter, Euler, Heisenberg, Schrödinger, Breit-Müller. All these people have been contributing to this field, but usually we call it Euler, Heisenberg, Schrödinger mechanism. And the fact that it's not reachable in the lab, but this field can occur around the compact object, or at the end I will tell you how new understanding, which is the talk of Jorge, will lead how we can produce this overcritical field in the physical setting, real physical, astrophysical setting. So the first idea, the line was that, so the easiest way to consider this Kerr-Newman charged black hole. Then we noticed that charged black hole, we knew this, it doesn't exist in the nature. It came with the idea of Petro-Wald. We introduced in our group the concept of effective charge. And this effective charge around the black hole will produce this E plus E minus and overcritical pair creation, and this region, we call it the other region, is the basis for the production of this E plus E minus. So, and the idea of the other region comes with Ruffini and Preparata. In 1998, first time it was mentioned there in some papers. Then the other region with the generalized work with 2010 in the work by Ruffini, Vereshchagin, and Shue. There they calculated everything about the properties of system, how it can form and how it can be basis for the energy reservoir.
let's go to the evidence.
Yes. So let me, because I need this for the evidence, this historical line. So the idea is that when it forms, it accelerates. How it accelerates? Two mechanisms, two channels. It is thermally driven self-acceleration, or it can be magnetically driven acceleration. So, and why why we need some self-similarity of this? Because it doesn't go to the transparency part, because we have this compactness problem. It needs to go to the transparency region to radiate. Why we need to this iteration? Because we have this effective charge or around the compact object, or later around produced by some vorticity. It needs to kind of charge and discharge the system. So they go out one by one, and this is the evidence of this, that we need some thermal component discretely, one going out one by one. So this is the one we observe one by one, we should observe it. So the signature is this one. When it Okay, the signature is this one. When it reaches the transparency, we should have a black body-like component or black body and this continuum. And there are two questions that we answer. When we take a time interval, do we have some iteration? Do we have some small structure of the thermal component? And in the same time, it will answer, is there black body component real? Because when we take an interval, that black body can be superimposed by some band function, some other function. So this is a real test to see if the black body is real in this. Stopped working. So also this is, it's better to mention, it's also other people report something similar, like photospheric emission, that's very famous in the field. But the key point is this overcritical fit predicts this iteration that we should see in the data. And this can be kind of discriminator of the other mainstream black body component that can be predicted by other models.
Okay, this is the key point. Forget about the history. We have good reason, but this is the key point. We found a thermal component and an additional component in the UP. But it's not only that. It's self-similar. Can you go?
Yes. So
this is the key. The thermal and the water. Okay.
So the key feature is this thermal and non-thermal continuum, which is, as I told you, was the prediction of this Euler-Heisenberg mechanism. So we did for several GRB bright enough to do the data analysis.
This model, how the non-thermal emission is produced.
Excuse me.
Non-thermal. Because thermal, I understand why there's non-thermal emission.
Yes, you will. This is a fact. Okay. Now let's see another key issue.
Okay,
This self-similar.
Okay, we will discuss.
This is a fact.
Okay, so
and then, okay.
So how we do it? We take we find the longest time interval that has the black body. Then we ask two questions. Is this small black body present when we divide the time interval to the smaller sub-intervals? Second, that if we find in each time interval, it shows that the whole black body is a real physical thing. So we do the integrated interval the time to this interval to 2, to 4, to 8, to 16, and usually 16 we stop not because we don't find, because of the sensitivity of the satellite. Number of photons are not, our signal to noise is too low. So this is the lowest, but in principle, as I told you, we need a prediction from the model to find the, yeah, exactly. We need to find, the prediction is that I think we cannot find based on the technology, 10 to 8 of them in like 2-3 seconds, but it's not possible to find. But as much as we can, also later I will tell you how the new satellites can help us to find more. So this is the for the whole UP duration, not yet in time interval going down. As you can see, in the rest frame duration, it's around 60 milliseconds to around 10 seconds, and isotropic energy varies from 10 to 52 to 10 to 54, with this exception of 130427A, which was piled up. We were not able to do time result analysis. And as you can see, this is the ISO of the UP versus delta T of the rest frame of the UP. And as you can see, it's interesting that luminosity almost stays constant. So this also another hint that it should be related to some inner engine activity, some not related to the, it should be powered by some inner engine activity. So, okay. The first one that we did this data analysis is 190114C. So we went down layer by layer, and in all of them, statistically, thermal component presence. And this shows, again, I emphasize that the thermal component is real. It's not the superposition of the other non-thermal part like cutoff power law or band functions. And it shows that we see a sequence of this, which after presenting it, I will operationally tell you what is the meaning of self-similarity exactly. So this is for another GRB, as you can see, is the same. So, but the temperature almost stayed the same for 180720B. I have written in the, so 1807 yeah. Yes. So it goes down to 0.1 second. Also, this too bright GRB, especially 160625B, which is a very famous GRB, because it was bright, it helped, it was possible to do time result analysis also with this one thanks to this high brightness. Again, the same structure also in the another GRB 160509A. And also in GRB 240825A, which is later I will tell you also in JCAM, it shows the similar structure. But in all of them, this self-similarity means that
this is the most recent we have found, and it's very beautiful because you can see it's recent. It was done by one you a few days ago. We had the first spectrum, and then we look for the next next component, and it was present.
okay. So this is the strategy that we have done. In short, we divided each time interval till the moment that it statistically was significant, and it doesn't let us to do more data analysis. So also this is the evolution of thermal in the each sub-interval. It shows that the thermal component evolves, luminosity evolves, and the luminosity follows some power law behaviors. As I said, the luminosity of them follow some power law behavior, and the point is that what we call the self-similarity is this one. Let me we call the self-similarity. This thermal component exists in all of them. So it is still not, we have not examined some more mathematical thing to find this self-organized criticality, because we need to do for different energy bands. So this, by self-similarity operationally, we mean the recurrence of the spectral form in all time intervals.
How about the thermal to non-thermal ratio? Is it also the same?
Thermal to non-thermal ratio, in majority of them stay the same, but in one GRB, which we recently did, it's a bit less than the other ones. Yes, this is the. So, as you say, I don't go through this. So this, to show that in the literature also there are some observational for the thermal, but this constant luminosity and this recurrence of the self-similarity can be a good discriminator that system operates in this overcritical field, and this black body plus non-thermal persisting down to the finest time being is the prediction of this. So it shows that every successful GRB model for the UP phase, for this phase, should be able to explain this behavior. So it should be able to explain how it can happen, which is the, I cannot say trivial, but it's the natural outcome of this Euler-Heisenberg and around near the compact object, but not, Jorge will discuss this.
Why can't the photosphere model?
There is one thing, the luminosity, when you scale them, luminosity stay constant in the UP for all of them.
So if the outflow has a constant luminosity, and at every moment the outflow goes through the photosphere to radiate the same luminosity.
So there is another point about this, let's say, subphotospheric. As far as I remember, it could not predict something, a small thermal component. So it's like my mind doesn't have a lot, but this comptonization will overlap will make the overlap all the thermal components. So we cannot, yes, so we cannot resolve it in that model. But here, as I said, naturally comes out. So, but still.
And is by far the most energetic emission of the GRB. The initial, most energetic emission from the GRB.
So, one of the most important part is that from the theoretical, which I didn't go through it, it allows to have 10 to 8 successive pair plasma, small thin shell plasma, but this is from the theory. This is the upper bound, but usually it can be even 10, 100. So this, from the theoretical point of view, we can expect 10 to 8 in 2-3 seconds. So it allows us to have, but it's very hard to have in the real observational setting to have this. So that's it. So the observation is not very simple, but it has very strong outcome and prediction of some electron-positron pair production. And in principle, we can search for time variability. Also, this minimum time variability Usually not always, it's the signature of central engine. I will show you some new observation, how it is again in line with this UPE phase. So I don't go through this detail because Jorge will talk about them, but to show that UP is almost the most powerful part of the GRB. When you represent the energy for other parts, it's almost UP always the most energetic part of the GRB, except for some. So it's worth to study more these properties of thermal component, and which we have been doing as a historical line in our group. So this part, Jorge will talk about it, so I will not go through it, because immediately after my talk, he will explain about this, how this happens, how this vorticity makes the this overcritical field, all this thing he will discuss. So briefly, I mentioned these new observations of the Chinese satellite that I have been working with. I will bring 3 examples that I have been working from the Inside HMT, GCAM, and SWAM, and usually they are able to observe better than, especially GCAM for PILAB, it's able to observe better than Fermi GBM. For example, we did for this, the left one is the one that for GRB that is in the UP system. Again, with this, we could find a better resolution thermal component by GCAM. So it was promising to find, even because of the high resolution of the satellite, to find a better spectral component and the spectral evolution of the system. Also GRB 250706, which we recently published in the APJ letter, it shows that this time, minimum time variability is energy independent again, and there are some thermal component there, again, relating it to the some inner engine activity, which there it's some interpretation also can be related to some accretion, as also in our model we can explain this. But finally, one very interesting part, the thing that we discussed, is about MEV line. MEV line, it was very interesting because many groups also, you have worked on it, related to pair annihilation from this E plus E minus. But again, if we consider this E plus E minus is from this UPE phase, it can be another indirect confirmation that this line can be indirect manifestation of that overcritical field. That is one line. But again, there is another thing that we recently published in Nature Communication Physics. So we, in parallel with, propose that it can be the first manifestation of the ultra-relativistic nickel that has entered in the ultra-relativistic part of the GRB. So again, it can give us good understanding of the GRB, and especially either the overcritical field or the nickel, which for our model here, binary driver hypernova, both things are critical. So more, it's more interesting. And the fact that this paper got accepted because we found the second line that other people lost it, and this second line can be only explained by different branches of nickel, ultra-relativistic nickel. So that's the point. But still, we should check this possibility of the overcritical, because also there are many papers about it, that is pair annihilation, and it fits better in the luminosity, in the best fit. So they are competing, we should see that. And the reason they didn't publish in Nature was the significance of second light was not very good. So that was the. So that's it. I think during the talk, the conclusion of everything I discussed many times. So this self-similarity, as I said, to before forget also there is a new GRB by JCAM 230307A, which has high resolution, maybe shows this self-organized criticality, which I'm working with the JCAM team to realize this. Thank you.
Rahim. We have time for one or two questions.
Okay, thank you very much for this motivating talk. I have a couple of comments and one question.
Yeah.
A couple of comments. You mentioned that Schwinger field has not been reached in the laboratory, but polarization of vacuum has been seen perfectly in the experiments with ultra-peripheral collisions of high-energy ions, nuclears, and in laser charged beam interaction. Multi-photon Breit-Wheeler process has been seen perfectly 30 years ago. And then about supercritical field, I'm interested very much because if I'm working on how to reach it under the laboratory conditions, I have some ideas, and with my colleagues we are working and publishing first papers. And let's discuss together what to do and how to understand. And then the question about what is of interest for me, I don't know the answer, but maybe you know. You mentioned several times Euler-Heisenberg Lagrange electrodynamics, but in the textbooks it's written that this theory is valid when electric field is substantially lower than the Schwinger field. But you say about supercritical field. How to resolve this problem?
In principle, the point is that I don't remember well, but I think what we worked was magnetic field was the main driver. But the point is that this electric field should not be vanishing in any, even the small thing is the point that the E dot B to not be zero, the magnetic field. So magnetic field will does the job, provided that in any case the electric field is not zero. So the.
So that's another question. Yeah. Magnetic field doesn't produce a loop.
Yeah, that's true. But it's.
But if you rotate, electric field appears. But then the question is, what is the topology of this magnetic field according to original ideas by Ramo about charged black hole?
No, that's not.
Then no problem. But if it is rotating, what is the topology of the electric and magnetic field? Electric field is not zero, but what is the Poincare invariant F? You said about E dot B, it's G not F. What's the topology of this invariant F? Curious to see. Maybe you have.
Yeah, no, I think this you have. Yeah, it's the topic of the.
We have to. Okay. The most important point at this stage is to clearly see the self-similarity process. This is, in my opinion, once you will reach, that is an opinion, the overcritical field in the laboratory, you will see also this. But let's not wait for that day. But let's just learn as much as we can.
Yes.
First, the key point now it has to do with black holes or not. It has to do with the general relativity or not. It has certainly to do with gamma ray burst, certainly. But the point is, and we will discuss this during the week, because we have quite an understanding. Let's go to the next talk, because we are trying to understand, without the black hole, a similar process. Within the BDHN model, because we know, thanks to, the BDHN model has been revolutionized by a lecture given by Michel Mayor here 2 weeks ago, that he showed us that all the work of fast rotating object should be forgotten, the way that was clarified by Hoyle long ago. But this is a different problem to understand better our BDHN model. But this is booming. Now, let's focus on the next topic, to show a way to obtain this without using the black hole, because it precedes the black hole formation.
But in all these years, all these works, in all of our work, we have presented how the magnetic field, because bit by bit we needed to more realistic solutions. So how magnetic field, usually we use invariance to represent this, but how magnetic field lines are formed, how they look, what's their topology. But the bit by bit, it's not one
talk.
work. It's starting from charged black hole to.
Let's go. Oh yeah.
Yeah, thank you very much for this very nice talk. I have a question. Why do you have this dynamic range varying by a factor of almost 100? What is driving this? What is driving this time scale? The time scale of this emission goes from 0.06 to 10 seconds. So my question is, what is the driver for these differences of time scale?
It's the observational. In principle, we should see one by one, but when it's observational effect here. We take for our analysis from 1 to 10 seconds, for example, then we find it. Then we ask ourselves, if it is real, then we go down, down, down to see it. The fundamental one are the small ones.
Okay, so it's just a matter of to have enough photons. Right?
Yes, exactly.
Okay, I get it.
It's a fantastic machine. To me, the key point is that self-similarity need linear theory. You cannot have self-similarity in general relativity. Therefore, this precedes the black hole formation. And please allow people to speak.
Let's go to the next talk. Your Gerweda, dark matter effect in compact object.
No, there's a new title. So good morning. So this discussion was, of course, introductory and propedeutic for this talk. So I will continue this line on the ultrarelativistic problem emission, more from the theoretical point of view, and with an application to the GRB 220101A. But as Rahim mentioned, this one of my goals here is to put this into the context of the the whole astrophysical picture of the GRB model. In this case, the binary-driven hypernova model. So this has been a long way to construct the binary-driven hypernova model for more than 10 years today to construct the timeline. So it is the progenitor of this in this model is a binary, even we have been discussing now as a possible extension of it, but current status is this one. In the massive binary, there is a second supernova stage where this binary can be very compact. And then, so we have a supernova. I think the pointer is not working. No. Okay, so at the second supernova stage, so we have a supernova explosion in presence of a neutron star companion. And this binary can have an orbital period from -2 hours. And under these conditions, that could be, there could happen many processes, transient process, characterized by a sequence of, by a series, by a time sequence of episodes, as Rahim mentioned already this. And so I have a video here for one of these simulations. So we have been bit by bit constructing a model with simulations. Here you have an explosion. This is a simulation with an SPH code. It's a modified version of the SN SPH code of Los Alamos National Laboratory, modified to handle supernova explosions in binaries by one person of our group that will be talking on Friday on this. So we have the explosion, the supernova going into the neutron star companion. This neutron star companion is going to accrete matter, and one of the key points here you see already in this simulation that you see the formation of vortices, higher angular momentum around the neutron star companion. So in this code, you have this supernova explosion divided in many pieces, in many pseudo particles. This is a simulation with more or less 6 million particles. And we tracked the thermodynamic properties of the particles and gravitational interactions with the neutron star companion and with the central object, with the newborn neutron star at the center of the supernova. And it's coupled with a general relativistic code that handle the evolution of the neutron star structure in axis symmetry. From everything. Everything. So accretion happens on both. There is fallback on the center.
How many solar mass per second?
Up to 10 to -2 solar masses per second.
Should be smaller.
And so there are emissions connected with the initial expansion of the material of the supernova. There is an emission associated with the accretion process on the star. There's accretion, and there is a ultraelastic prone emission phase, and I will speak about today. And we expect to happen as this material around the neutron star companion is accumulating with large angular momentum and with a huge magnetic field will create the conditions for the process that Rahim was talking about. Then, of course, this neutron star will, depending on the binary properties, can reach conditions for collapse into a black hole. And there will be emission associated with that black hole in presence of those of this environment. So this is a three-dimensional picture of this binary. This work also has been made in collaboration with Chris Fryer. That if you go to the basement of ICRANet, you will see his signature with the hypercritical accretion drawing of this model. And Laura Becerra is up there, picture there. So she will be talking on Friday. This is just a snapshot of the latest simulations in the paper of 2024. We are including also rotation, rotation of the initial rotation of the compact neutron star companion, and they are also exploring different outcomes, different nuclear equation of state for neutron star and so on, time of collapses and different things. Okay, I will move now to in this whole timeline and time sequence of episodes, there is this most energetic episode of the GRB, that is the ultrarelativistic prone emission, and this is the light curve of GRB 220101A. This is one of the most energetic GRBs so far, with an energy, isotropic energy release about 10 to the 54 erg, as you see from this table. So I don't have the time to go through all these these episodes, so only I will focus on the third episode, that is the UPE phase, which, as you see, has an energy of almost 10 to the 54 erg. So, so we are speaking about this electron-positron pairs formation. It's from long ago already, for more than 20 years, that it started this series of simulation of this plasma of electron-positron pairs going into some material of baryons, and to show that this could lead to MEV emission with features as those observed in the in the UPE phase of the prom emission of the GRB. So the idea is that you have these electron-positron pairs that are created and later thermalized with an electron-positron photon plasma. They expand, and they engulf baryons from the environment, and then this electron-positron photon baryon plasma reaches transparency with high Lorentz factors, and then they emit these photons have typical MEV energies. So there are several papers going to this into this physics, and the idea is that you have these electron-positron pairs going into the baryon plasma. This is a simulation of this electron-positron pair going into the ejecta of that I showed before. This was made a few years ago by Juan David Melon Fuchsman in our group with a modification they call Pluto to handle these kind of systems. And the idea is that then you have this plasma reaching the high Lorentz factor, then engulfing baryons, and then again reaching a coasting phase with high Lorentz factor. And it is possible to show that the Lorentz factor it has a relatively simple way, simple formula to explain it. It depends on these quantities, so it depends on the thickness of these system where these electron-positron pairs are formed. So the thickness of what Rahim was calling the diode region, depends on this also on this ratio between this energy, this epsilon b beta. This is just the ratio of the observed thermal component of the UPE phase relative to the total isotropic energy. And there is also, you can estimate the radius of transparency, and this the parameter is the baryon load parameter. Is essentially the amount of mass, of rest mass of baryons engulfed by the electron-positron plasma divided by the energy of by the isotropic energy, so the energy, the whole energy of the electron-positron pairs. And so then what we started was to, what would be the source of these electron-positron pairs? And so first idea was about, of course, QED vacuum breakdown. Rahim already mentioned this. First idea in 1975 by Dabur and Ruffini, then moved to 1998 in the case of the radial-Nostrum solution. So the first idea was charge of black holes. There is the electron-positron, the pair rate. This was mentioned by Bulanov before in this question, how it moves. When you have a magnetic field, of course, this you have to compute it correctly with the correct electromagnetic invariance. In this case, these electric and magnetic fields, they are in the frame where they are parallel in such a way that they you have the correct use of electromagnetic invariance. So this is a radial-Nostrum and the Kerr-Newman solution. This was a first step. And then we move to more realistic because, of course, these black holes are not isolated. And so we talk in at least there is a magnetic field, and at least they rotate. And so there is the problem of Faraday induction in the Kerr black hole. So you have a Kerr black hole in the magnetic field, you will have Faraday induction and induce the electric field. And it's this electric field eventually that can break down vacuum and create pairs. And then, so we went to this concept of effective charge that is not needed, but it's a good concept to relate this kind of work to the previous one. If you go to compare what is the electric field produced by these kind of configurations, okay, and you see actually that this induced electric field along the pole, it decreases as Q over R, as 1 over R squared. So if you compute that term, that Q, that would be effective charge, because it goes as 1 over R squared, and you estimate this for these kind of setups that we use in GRBs, then you see that the charge to mass ratio of that effective charge is similar, in fact, to the charge that was used in this kind of configurations to explain GRBs at the time. So that's why it was important, this Q, this effective charge, just to make a connection. But yes.
If field is external magnetic field.
If you?
Magnetic field is external?
It's external, yes.
Where does that?
It's external.
Where it comes from?
Oh,
Companion?
so no. We are assuming that it stays from because this black hole is formed from the collapse of the neutron star. So it's fossil from the neutron star, at least transient. And it's transient, but it can be sustained also from the material around, eventually.
So the amount of charge depends on the strength of the E field.
Absolutely. Right? Yes. Huh. So, and then, so in this kind of setup of black hole, we made this work last year where we make a theoretical treatment of this region of electric positron pair creation that is an invariant formulation of this problem because of the, we're aware of this problem that just Sergei Bulanov was mentioned before. Here you have a magnetic field and electric field, and so you need to have a correct formulation of the problem of electron positron pair creation. So it was done this paper, and we compute the energetics of this the other region. So and we see this is magnetic field in units of the critical field, so in units of a field of 4 times 10 to the 13 Gauss, and this is the energy that you can have in this region for different values of the black hole spin. So it can be huge. It can be down to 10 to the 52 Earth in this, and you can compute the density temperature, energy density temperature of this plasma that would eventually be initial conditions for a simulation. So, but it's relevant for me now here is are these two conclusions from that paper. So the first one is that the treatment could be extended to a neutron star, so that this is not at all something that could happen only in black holes, because the essential ingredients is that you have a magnetic field and rotation. So also neutron stars are good laboratories for that, and there was an estimate that you can easily get those conditions, and so we promised there to do it for neutron stars. And the second, that this could also happen in neutron star mergers, because you form either a neutron star that is massive and highly rotating, or even you can form a black hole also in presence of magnetic field. We first went to the second conclusion, and we make a review model for the short GRB 090510. Where we make all the reanalysis, because we already studied this GRB in 2016, okay, with the pre-all model. And then here now we review it with this UPE phase of that GRB, forming that case with a black hole with a magnetic field and with the rotation creating the electric field for vacuum breakdown. And then we go now to the first conclusion that this could be extended to a magnetized rotating neutron star. So the idea is that it takes some time for the neutron star to get collapse of the black hole to a black hole, because you have also these what we are been showing in these simulations is that these vortices I show you in the first slide, in the first video, they carry a lot of angular momentum. This is a cut of the specific angular momentum, so angular momentum per unit mass in the gravitational capture region of the neutron star. It can be huge, so it can be this angular momentum over m squared is larger than 1. This is a first signal that you cannot form a black hole with such an amount of angular momentum. So this angular momentum has to be dissipated before the star can go to a black hole. If you go to the maximum angular momentum over m squared of a neutron star is 0.7 even. So you cannot go to that. And the rotational energy is of the order of 10 to the 54. So the idea is this amount of rotation, this angular momentum, this rotational energy, they have to be dissipated and can power this UPE phase before black hole formation. So this is a simple model of it. This is characterizing the diode region of a rotating neutron star. So we have there the solution of a rotating dipole. This is a Ruffinian Trevisan 1973. It's simple, but it shows all the features that we expect. So essentially, we have the star rotating with some angular velocity, and you can extend again the treatment of this. The other region here is the use of the electromagnetics invariance to compute the percreation rate and all the properties, and to define what is important here, the geometry. And so you can define this, the radius of this region, the region where pairs can be created. And the important thing here is that from this formulation, you can derive that there is a minimum magnetic field to create pairs in these configurations. And it depends on this parameter. This parameter is the angular velocity of the object times the radius over c, omega r over c. These relativistic parameters of rotation. And if we move to an application to a specific number, just to give you some numbers to put this on ground, GRB 220101A. So how can we determine the parameters? How to, we have this whole picture and we have to put these numbers together. There is a table up there where we give the estimate parameters of the black hole that is formed in this GRB. How do we do that? That would be another talk, but we have already given some talks during these previous Zeldovich meetings about that. The idea that the black hole that is forming the GRB emits a GeV emission by accelerating charged particles. And from that, and that this is powered by the extractable energy of the black hole. So from the GeV emission, from the GeV energetics, we derived what would be the mass at the spin of that black hole. So we have inferred that that would be about 2.4 solar masses, and the spin parameter will be of the order of 0.4. Since that black hole comes from the collapse of the neutron star, then these parameters can be used as values for the critical mass of the neutron star that collapsed, and the spin and the angular velocity of that neutron star at the time of collapse. So our estimate was 7.4 times 10 to the 3 radians per second for the angular velocity. And so that leads to this minimum magnetic field to have this pair creation around this in this vortex. So it will be 1.12 10 to the 14 Gauss. This is the minimum magnetic field. It's not exact. Magnetic field can be higher. Certainly cannot be lower. Okay, to have a UPE phase. It's a nice number for an astrophysical setup of a neutron star. And then we can estimate the energy of the pairs. In this case, are a few 10 to 43 ergs. So it's not the whole, because as Rahim just explained, we expect it to be several transparencies, a sort of train sequence of transparencies that happen. So this electron-positron pair creation going on and repeat over and over and over many times. How many times? So the UPE energetics is out of 7 times 10 to 53 erg. This is what is observed, the energy release, isotropic. We have estimated beaming factor of the order of 0.01 from the geometry of this diode region. And so we have to explain more or less 10 to 7, 10 to 10 to 51, which means that they will be of the order of 10 to the 8 events that should compose that UP phase. And that was the order of magnitude that Rahim showed in his talk. We have made this sort of analysis for the other GRBs, and they show similar numbers. From that, by the way, this angular velocity that we are there inferring from the black hole, you see, is compatible with what is inferred from our simulation, okay? From the simulation of the vortex's angular velocity, that is for the order of 10 to the 4 around the neutron star. And then, so we can infer what would be the Lorentz factor, the baryon low parameter, and the transparency radius of in some of these sub-intervals, let's say, of the light curve of this UPE phase, where there is enough statistics to do it. I have just 2 examples of here. This is slides 4 and 6 of this of the light curve of the GRB, where we could identify the black body component associated with the UPE phase, and there is the parameter of this black body to the whole UPE energies of the order of 0.3. Is more or less the fraction that Vincent was asking before. What would be the ratio of the black body to the whole energy, to the more or less 0.3, also for the other sources. There are with the parameters that we derive for the temperature, the Lorentz factor, the baryon loading, and the radius of transparencies. So consistent what we expect for this system and with our previous simulation of the plasma going into the supernova ejecta. So I'm going to the last thing. We'd like to mention some limitations and perspective. Of course, we are starting. And so we have used a relatively simple electromagnetic field configuration. There can be higher multiples, twisting magnetic field, and other kind of complexities in the electromagnetic structure that we can model. We can go into that. We have used to derive this Lorentz factor, transparency radius, and so on. We have used the theory and what we know from the simulation of the electron-positron plasma expanding spherical symmetry. But we have seen that this diode region is not spherical. So we have to go into a simulation at least in axial symmetry. And so it could lead to derive consistently the collimation and the maybe higher relativistic jet emission. So we have to go into that. We have seen also from our calculation that the magnetic pressure is comparable to the plasma pressure. So we probably have to go to a magnetohydrodynamic simulation of this system, and this could be also the inclusion of this magnetic field in the simulation. We have to see if it could also be a key for non-thermal component. Then, for given magnetic field, The lower the rotation, there is the lower temperature of the plasma. And then if this, the transparency of the photons shares that hard to soft evolution, then there could be a decrease in photon peak energy. In time resolved spectral analysis, you have to check that if that happens. And so I have only two main conclusions, I think, from this presentation. The first is no need of black hole to produce copious electron-positron pairs. Rotating magnetized neutron stars. So this is, of course, there is a minimum magnetic field for given rotation, or there is a constraint on the magnetic field and rotation to do that, of course. But in GRBs, that would be, or these barrier-driven hypernova modeling are easily achieve these conditions. And then there is enough high angular momentum in the accreted material to inhibit first a prompt black hole formation. So to delay black hole formation for a few seconds, and then this UPE will be powered by this dissipation of angular momentum by these pairs. So these are two conclusions. So, thank you.
Question?
Is a delicate moment because I fully agree with these conclusions. And at the same time, it's difficult to see the simplicity of these conclusions. If we put in the physics of black holes and all the work that we have done in ICRANet on the magnetic field of the black hole and the electrodynamic of black hole, this is not relevant in this. Therefore, is simplest, this conclusion. There is no need of black hole and all the things that we heard before, and which is splendid work, which will be covered in the next day. But my point is, for this presentation, this is the key conclusion. It precedes the black hole. Therefore, you cannot use the black hole work and electrodynamics to explain this. This is simpler and highly enough angular momentum to do the UPE. The enormous beauty of this result is that it precedes what will be happen in the laboratory as soon as you will be able to create this condition. You will see the self-similarity. And this is the beauty of these two presentations. This conclusion and the fantastic one, the previous one by Reim. Where are you, Reim? Okay. And just maybe if you can show one last time this self-similarity in order to keep that in the mind of everybody in your talk, the self-similarity and which can be explained that's very simple by the presence of the magnetic field and the vortex of the material in the early phases. But for this, you need a lot of kinetic energy of the supernova injected by the supernova, and that needs the model of OBA. But fortunately, we have a few more lectures during the week to point out that. Maybe if you can show one of the self-similarity to leave everybody either from you or from Raim, to leave everybody clear of the self-similar structure and well, wherever you have. Yes, there, that one. This is the fantastic result. The clear self-similarity and the fact that this must come from electrodynamic, not from general relativity, not from black holes, is previous to the black hole formation.
I have a question, continuing what you said. George, thanks first of all about your presentation. And what is the time scale of the collapse? And then when you reach the conditions during this collapse of strong electromagnetic field, electric field, you start create electron-positron pairs. And this electron pairs was said by previous speaker and by you, they result in shielding of the electromagnetic field, absorption of electromagnetic field. What is the time scale of collapse and what is the time scale of shielding of the field? I guess you have estimated this.
Well, the time scale, here the time scales vary from system to system. It depends on the conditions of the binary. Okay, that's in the speaking about the time of collapse, the delay of collapse. It can be a few seconds, for example, to reach the collapse phase. But when you reach the point of collapse in this picture, the black hole is formed, but the magnetic field and the rotation is such that they don't anymore create a high enough electric field to create the pairs. This is in this picture. It's like that. You can it can accelerate particles. These particles can emit the GeV emission and so on after the black hole formation, but they cannot produce pairs anymore. So the pairs formation is confined to the first part when you are dissipating this initial angular momentum.
I see. Thank you.
Thank you for interesting talk. Do you take into account possible neutralization of electric field due to external plasma?
Okay. No, because in this simulation, what we have checked is that it's still in a low density environment, still in around the black hole. You see in the simulation, there is one key point, and this is a good question, that I don't show here, but that we have we track in our simulation. That is the density. It's 10 to the minus 4 grams per cubic centimeters. It's extremely low and well below Goldrich-Julian density. So
yes, thank you.
Thanks for interesting talk. Just a brief question regarding the optical thickness of the system, because you create electron-positron pairs in extremely strong magnetic fields. So wouldn't that completely block any escape of the gamma rays that you need to explain the GRBs?
Yes, this is included in the simulations in the sense that this pair creation rate is extremely fast. Thermalization is extremely fast. This was shown some years ago by Gregory Vereshchagin and Alex and Professor Ruffin in a paper. So you create this plasma and it's optically thick. So in this expansion, and then it reaches transparency, and with a high Lorentz factor. So only there can escape photons. In fact, before is highly opaque. This plasma. So, and the time scale of transparency, radius of transparency, everything has to fit, of course, the time of observation of this MEV emission and so on. So it's included there. So you're right, but it's included.
So the next speaker is Bing Zhang, the physics of fast radio burst.
Careful, because I was just informed that down which is unfriendly toward the broadcast.
I can use this one too. This one.
Not inside, but outside.
USB-C Type C. Okay. So
This one.
that should work.
Okay. You see internet, sir? Internet?
No need. Ooh, that's my family. Okay, good. Can you hear me? Okay. Thanks, Remo and organizers, for the invitation. And my name is Bing Zhang. I have been working on gamma ray bursts over the past 20 years. So stayed in University of Nevada, Las Vegas for 20 years. And last year, I moved to University of Hong Kong. So initially, I planned to talk about the GRBs, fast exit transients, the FRBs in this talk. And Remo and Gregory offered an opportunity to talk about the other two topics in the evening at a public talk. So this 35 minutes, I'll focus on fast radio bursts only. Okay, so we are living in a dynamic universe. You can see all these images. No need to explain things here. So we have black holes, compact objects, neutron stars, and all these transients are observed in gamma rays, X-rays, optical, and also radio. So fast radio bursts are the newly discovered these transients in the radio band. It's newly relative to GRBs. It was published in 2007. And these three distinguished scientists got the Shaw Prize for the discovery of fast radio bursts. So I'll talk about the physics of fast radio bursts and publish these three review articles. The first one is the short version published in Nature in 2020. And this one is 2023, so this is a more extended version published in the Reviews of Modern Physics. And recently, this is the annual review of nuclear and particle science, talking about multi-wavelengths and multi-messenger counterparts of fast radio bursts. So this field is very exciting because we are, from the very beginning of understanding underlying physics, just like a detective, we are doing the job and using fingerprints, footprints, and the smoking gun to really identify this cosmological crime site. So, so we should respect the data. So that is very important and remove theoretical prejudice. So regarding data, I want to acknowledge my colleagues. So this is China's 500-meter radio telescope, also called FAST. And I led this, me and Weiwei Zhu from 2020 to 2025. We have this 5-year key science program. So we have 100 members from 20 institutions, published some papers in Nature and Science, use the fast data to really constrain the FRB physics. And I also want to point out CRAFTS and the GPPS. CRAFTS is led by my friend Di Li, who will give the talk after a break. So in order to tell the physical process, let's go through the observations. These are the fingerprints, footprints, and smoking guns. So what we observe, and then we can figure out what they are. FRBs, let's start from temporal information, and then we talk about spectral information. And temporal information, so there are bursts, and they're very, very short compared with GRBs. The duration is only millisecond. Okay, only millisecond. And this was the first discovered one. It's called the Lorimer burst. So you can see the spike is only millisecond. Of course, because it's in radio wave, the arrive time scale is different. It's frequency dependent. The high frequency ones will arrive earlier and the lower frequency one will arrive later. This is called a dispersion. That's due to free electrons in the universe. Usually what people do is to de-disperse to correct for this delay, the so-called dispersion measure, and then get this sharp spike. And this is a very bright one. You can see it's a very sharp single pulse. And then later, people found that some of them are repeating. So most of them are just one-off, but some of them are repeating. So this is one single source. They have many pulses, maybe separated by seconds or even hours. You can see this one, there's a structure. So there's not one single pulse, there are two pulses, which means it's not one-off event. You must have a central engine. So in terms of spectral information, so FRBs have been detected in 110 megahertz to 8 gigahertz. This is for different bursts. So for individual bursts, the actual spectrum is quite narrow. Sometimes it looks like a Gaussian. But you can see there's also multiple peaks and there's something like downdrifting. So the early pulse is a little bit higher frequency, and later become lower frequency. And you can see some of them are aligned there, like 11 of them lined up together for a repeater. Polarization is the key. So most of these FRBs have extremely high polarization, nearly 100% linear polarization. So this tells us that there must be very strong magnetic fields in the emission region, and the only other objects in the universe have 100% linear polarization are radio pulsars. And we know the pulsars are in neutron stars, very strong magnetic fields. So, and the polarization angle actually, sometimes it is stay flat within the single pulse. The polarization angle is not changing, which is the magnetic field configuration is not changing. But some other cases, you can see they go up and down, it is changing. So it is very complex behavior. And with polarization, one can define something called a rotation measure, RM. So rotation measure is the convolution of the magnetic field along the line of sight and also the density and the column integration of that. So this RM is telling us the immediate environment of FRBs. So if you have a stronger B field near the FRB, or you have a denser median near the FRB, you have a larger RM. And interestingly, this RM is actually varying. So this is one repeater repeating FRB. It is go up and down, and sometimes it stay flat. And this one, it goes up and down, suddenly RM jump by a factor of 100 and fall down. So it tells us a lot of dynamical process is happening near the FRB sources. So these to us suggest that maybe they're in a binary system. So for example, this thing is the CME, coronal mass ejection from the nearby star, and hit some magnetic blob and reach our line of sight. So this is the polarization part. And as I said, there's a dispersion measure, because just based on this delay, one can correct for this DM. And DM is actually the column density of the free electrons along the line of sight. By measuring DM, we immediately know that how many electrons are along the line of sight. And it turns out that most of FRBs are coming from, so this is galactic plane, this is galactic latitudes. So the blue dots are the radio pulsars. You can see near the galactic plane, we have more electrons, the DM is large. But FRBs are these guys. They're at high galactic latitudes, which means they are out of the galaxy because their DM is much, much greater than radio pulsars. So immediately it tells us that FRBs are cosmological objects. And indeed, when people start to localize the FRBs, so this is the redshift, this is the DM. So there's a linear correlation, and this is the most updated version. The higher the redshift, the larger the DM. So
The
larger dispersion measure, DM, dispersion measure. So just based on measuring DM, we can already estimate the redshift. So based on the measured redshift, I think it's 1 point something is already pretty high. But based on DM, we already detect some FRBs at redshift of 3. And people even suspecting that with fast we can probably detect redshift 6, 7 FRBs, but they're not confirmed yet. Okay, so with redshift we can start to talk about luminosity and energetics, and it turns out that there is a wide range of distribution, 8 orders magnitude. So the luminosity is 10 to the 38 to 10 to the 46 ergs per second. Isotropic energy is 10 to the 35 to 10 to the 43 ergs. So in radio pulsar standard, this is very, very large, very energetic radio emission. However, in the GRB standard, so this is much smaller. It's almost 10 orders of magnitude lower, which is understandable. So these are mostly not catastrophic event because they repeat. So you cannot destroy the entire engine like GRBs. And another interesting thing is the so-called brightness temperature. So this is defined as this formula. So it tells nothing about the real temperature of the object. It is just saying that if the radio emission is from a black body, how high the temperature could be, it is 10 to the 36 Kelvin. So this tells us the emission must be coherent. It really doesn't mean that temperature is that high. It's just that all the electrons need to radiate coherently to produce such a brightness. Okay, and I came from both views. So from radio pulsars, my PhD, I was working on pulsars, and then I spent decades to work on GRBs. And fast radio bursts, when it was first discovered, nobody knew what they are, so people just borrow this insight from the two fields and trying to figure out what is going on. And in the Nature review, I did this comparison between the two fields, GRBs and fast radio bursts. And actually, we went through all 4 steps to answer these questions. Are they astrophysical? Are there multiple types? Where are they, and what makes them? And it turns out that the FRB field already went through all 4 stages, and actually in a faster pace. So indeed, they are astrophysical. There are multiple types. There are repeaters and non-repeaters. And where they are extragalactic outside the Milky Way. And what makes them? So initially, I was very pessimistic because the energetics of FRBs is much, much smaller. How can you figure out what they are at cosmological distances? For GRBs, it's different because we can see a supernova associated with it. We can see gravitational wave associated with it, and we know that, okay, they are at least related to massive stars or compact star mergers. But for FRBs, they're so far away, essentially there's no way to tell what they are. But because they are so frequent, they're less energetic, there are a lot more of those guys, and one of them actually happened in our Milky Way galaxy. In 2020, only one galactic FRB was detected, and it came from the Milky Way, and it came from one magnetar. Magnetar is a neutron star of 10 to the 15 Gauss magnetic fields. So we know that at least the magnetars can make FRBs. Okay, so the physics of FRBs, we address these 3 questions: what, where, and how. And what the common, consensus within the community is magnetars are probably doing this. Nobody can say that all the FRBs are made from magnetars, but at least we know that some of the FRBs has to be made from magnetars. And then where there are 2 types of models. So as I said, the people from the pulsar field, from the GRB field, all came to the field to work on this. And the pulsar people said, okay, they're magnetosphere, and the GRB field, okay, they're like shocks. I came from both fields, so luckily, so I can judge which is correct. I think this one is more correct than the other one based on the observations. So these are the components of FRB models. So when people write theories to explain FRBs, there are two distinct, actually, questions. One is the source. So what is making FRBs? So this one, we have repeating models, we have non-repeating models. Repeating models, we have magnetars, we can have other things, pulsars, interacting neutron stars. Non-repeating, we can show mergers, blitzars, those kind of things. And another component is talking about coherent radiation, because as I said, the radio brightness temperature is so high, so you have to come up with some mechanisms, either inside the magnetosphere or outside the magnetosphere, pulsar-like or GRB-like. So one can talk about antenna, just like what the antenna is doing. All the electrons are macroscopically, globally oscillate together and radiate as a huge particle. So the emission power, instead of this n times of the individual power, it is n squared times of the individual power. So that's why it has become much brighter. And then there are plasma lensing maser and vacuum maser. So this is kind of amplification of certain process. So if the plasma, before radiating photons, already start to amplify the process, this is called plasma instability, then this is called a plasma maser. Or you can already produce photons, and photons got negatively absorbed, which means also amplified during the propagation. So this is a vacuum laser. So there are so many different models in this side as well. Then the question is, what should we do? So there are two ways. One is the bottom up. For example, some people like, okay, I like this model. Let's just start upwards and model this one. And another way is, okay, let's go from the observations and try to rule out different things. And eventually we narrow down, okay, it is magnetar, it is antenna, for example. So this is the approach we are doing because we have FAST, we have the observational data. Okay, very quickly go through what, where, and how. So what is sources and source progenitors. So it is related to this side. So as I said, we already narrowed down, it is magnetar. So what? So magnetars. So this was the famous FRB detected in the Milky Way. It has two radio peaks. And then it came from a magnetar. And that magnetar radiated an X-ray burst. And you can see this is X-ray, but this is HXMT. Rahim just said that this is a IHAP vision. And so we had a campaign. So I used the FAST and Shangnan used this. We jointly observed, but unfortunately during this FRB, FAST was not pointing to it, but HXMT was pointing towards it. And very interestingly, this X-ray burst had two peaks. And those two peaks actually temporarily aligned with these two radio pulses. So it tells us that indeed, the radio emission comes from that magnetar X-ray burst. So that was the breakthrough in 2020, and our paper was listed as the top 10 breakthrough of the year by Science magazine. Okay, so what? Let's say they are magnetars, but what makes the difference between active repeaters and non-active, say for inactive or single one-off bursts? If they are all magnetars, something have to make the difference. So this is our consensus sort of speculation. So the top one is our key science collaboration, and bottom one is Binyamini and Kumar. So we more or less reached the consensus that because neutron stars have the spin axis, also have the magnetic axis, if the two axes are aligned to each other, then and turns out that axis beam towards the Earth, then we start to see this burst all the way, then keep repeating. So that is our idea of having these active repeaters. And interestingly, out of the, say, 10,000 bursts we detect, we couldn't detect a period. So that's very puzzling. For pulsars, once you have like hundreds of pulses, you can measure the period. But we never measure the period from FRBs. But this model tells you why. Because if the two axes are aligned, there's just essentially no period, because this lighthouse beam points to us all the time. So there's no way that you can see that period. So that is our suggestion. So this was, we went one step forward. So we had two papers with my student. So we look into the population of magnetars in the entire universe doing the population synthesis and look at, okay, only 4% of the magnetars are in the binary systems. So these are different channels of forming isolating magnetars or binary systems. And then we said, okay, if there is a companion, the companion wind can help to align the two axes. So it is not a coincidence. So with a companion, it is more likely that the magnetar has the two axes aligned. So this is why these active repeaters have these puzzling RM features, right? So go up and down, and this CME, coronal mass injection, it means that there's something else is near the magnetar. So we interpret the active repeaters as the magnetars in the binary system with the companion doing something, not only say align the two axes, but also send some mass material to change the RM. And we even suspect that it might be the trigger to make it more active. So this is what, and then where and how radiation mechanisms is more difficult. This goes to this side. So what is this side and where's the inside and outside magnetosphere? And there are different mechanisms. So how do we do this? This is another brief introduction why this is so essential. The brightness temperature is 10 to the 36 Kelvin. So this means it must be coherent. Coherent radiation is the most complicated radiation process in the universe. So in that table, I listed 4 mechanisms from simple to more complicated. Black body, everybody knows, both photons and electrons are in thermal equilibrium. And thermal radiation particles are in thermal equilibrium, but photons may not. And then we have non-thermal, the particles are accelerated to power law and photons are not in equilibrium. But the coherent non-thermal means not only the particles are, say, non-thermal, they need to work together to generate something coherent. So it's more difficult and it's more, it has been a 50-year puzzle in the radio pulsar community. What is the coherent mechanism for pulsars? And FRBs just amplify that problem by another 10 orders of magnitude. So instead of doing, we stick to a particular model and work out what is going on, we actually use the data to do the constraints. So whether it is inside the magnetosphere or from very far away shocks. And with FAST, we collected a lot of interesting observational properties. I don't want to get into details, but the bottom line is, for example, the first one I should mention, the radio emission aligns with the X-ray emission. And we know the X-ray emission comes from magnetosphere, so this tells us the radio emission should comes from magnetosphere. And then there's a polarization angle thing, so the swing and the 90-degree jumps, circular polarization. So we start to see all these features from FRBs, and all these features have been detected in radio pulsars. So that to me is very straightforward. So whatever producing pulsars is somehow more efficiently produce FRBs. And FRBs are from the magnetosphere of the neutron star. And the waiting time, so that is Deely's paper. I was also the corresponding author of that paper. And that was the first FRB source detected with FAST. So we detected more than 1,000 FRBs. And then there's double peak waiting time distribution. If you count for all the pulsars together, it turns out that energy is pretty large. It's already, if we assume that every radio emission has like a X-ray component with 10,000 times more energy, then the energy is already very high, close to the magnetar energy. So there's a energy budget issue. And recently there's another case that is even exceeded that number. So it tells us that if it is a shock model, then we run into the energy budget problem. If it is magnetosphere, the efficiency can be much lower, so higher, so which means we only have like 100 times more X-ray energy, then we should be okay. So this is another argument in support of the magnetosphere origin. And narrow spectrum, the observed spectrum, they're all like Gaussian. And if we measure the delta nu over nu, it turns out that observationally, this middle one, delta nu over nu is only 0.2. But theoretically, this is again from the GRB physics, there's a curvature effect. Even if everything is a delta function, the spectrum is delta function, because of this arriving delay and Doppler difference, the delta nu over nu has to be 0.5. So minimum is 0.5. It has to be wider than that. But observationally, it is only 0.2, so it is narrower. So this tells us any shock model just fails because shocks, they are spherical. Only in the magnetosphere, when you have very narrow magnetic tube, can survive. So that is another important support to this magnetism model. And people also did the scintillation measurement. One can constrain the size of the emission region. And it turns out this was from the Chime team. It turns out that the size is smaller than the light cylinder of the magnetar. So this is another support. And finally, we also see the evidence, something I call slow radio bursts. Fast radio bursts are the very narrow beam towards us. But what if that fast radio burst is slightly off axis, not beaming towards us? The luminosity would be lower, the duration will be longer, so I call it a slow radio burst. And it turns out that we detected, again, in collaboration with HX and MT people, we detected a slow radio burst associated with the X-ray burst. So this is our geometry. Fast radio burst is very narrow, X-ray emission is much wider, and usually we see in this direction, but in that direction, we see strong X-ray emission, but weaker radio emission, and that has been confirmed. So FRBs are also narrow, narrowly beamed, so this is also consistent with the magnetosphere origin. And in the field, there are theoretical discussions. Some theorists say that FRBs cannot escape, but they start with a FRB trying to get through the closed field line region. But this is not the physical model we are discussing. We are talking about open field line region, and plasma is moving relativistically outwards. Once we consider open field line region and relativistic motion, then FRBs can escape. Okay, so the conclusion of where there's just magnetospheres, how is more difficult, but at least we narrow down to these models. And I don't have time to get into detail, and because this hasn't been really proven, but my personal favorite, so I propose this model, is called inverse compton scattering. So we have magnetar, the crust cracking, so they will send out these kilohertz waves. But FRB is in gigahertz. How can you convert a kilohertz wave to gigahertz wave? So what we need is just to have some relativistic particles. the Lorentz factor of particles is about 600. And then we also need some low frequency EM wave, and it has to be a fast magnetic sonic wave or X mode. And that kind of wave can be upscattered to produce the observed radiation. Okay, so limited time, I'll move on to FRB as probes. So a lot of people don't care about what FRBs are, but they care about FRBs because they're cosmological distances. They can help us to constrain a lot of interesting things, astrophysics and physics. For example, cosmological probes, so they can directly measure the baryonic matter, so so-called omega B in the universe, and it turns out that it's about 0.4, which is consistent with the Big Bang nuclear synthesis measurements. And one can also probe the larger scale structure, IgM inhomogeneity, dark matter and dark energy. So we can use this DM because DM carries omega m and omega lambda. We also have Z redshift. Then you can start to constrain the dark matter and dark energy parameters, even though you need to combine with the type 1a supernova and other things to make it better. And we can also probe the reionization history. This is very, very interesting because DM measure all the free electrons along the line of sight. Suppose we, in the future, we detect FRB at redshift 7 or 8, then we measure the redshift. We know that it is there, but then we can measure the deficit of DM. If everything is ionized, suppose we measure DM, let's say 7,000, but what you measure is only like 6,500, then we know that the universe was not ionized back then. So DM would be, FRB can be very nice probe to study the reionization history of the universe. And one can also measure the curvature of the universe through gravitational lensing, turbulence, IgM magnetic fields. There are a lot of applications, and my group wrote some of those papers. And not only just studying astrophysics and cosmology, FRBs can be also probes of fundamental physics. For example, we can talk about Einstein's weak equivalent principle, because suppose different frequencies travel with different speed, then it will become wider, even if it is a delta function. When you observe something from very, very far away, and it's still very, very narrow, then you can measure the difference between that speed for different frequencies. And that is also a way of constrain the mass of the photon, because if there is a mass, then it becomes wider. So these things have been applied to FRBs and get very interesting constraints. Okay, so with limited time, so I'll put my conclusion here. So active repeaters are likely powered by magnetars in binary systems, and inactive repeaters are probably isolated magnetars. There could be other possibilities. Actually, tonight in my multi-messenger talk, I'm going to talk about the possible other channels and where magnetosphere origin, how, so I say inverse competence scattering and top-down approach, and FRB can be probes of the universe and fundamental physics. And finally, I want to advertise, we launched this HKIA, Hong Kong Institute for Astronomy and Astrophysics. So that was inauguration last year, November 3rd. And as Remo already mentioned, we will host MJ18 in Hong Kong July next year. Thank you.
Yes, thank you for for the talk. There is one question about fast radio bars. That is the population that you mentioned, not less, but about the numbers. Because observation, I think the observed rate is very high. It's like the order of 10 to the 5 per gigaparsec cube per year, something like that. So if we think about magnetars as the progenitor, what is the current status of, there is any tension with the numbers of magnetars that can produce from different channels?
There's no, so if anything is related to catastrophic event, as you said, then there's a tension because supernova has 10 to the fifth, and FRBs, it depends on the luminosity. If you really go down to the luminosity of the galactic one, it's 10 to the seventh. So definitely you cannot produce with the, say, catastrophic events. But with repeaters, then no problem. You can, for one source, you can produce tens, thousands of them. So magnetars should be fine.
But you reduce the population using this repeating.
Repeating, yes, yeah, yes.
Can I ask, early on you talked about the relation between the dispersion measure and the redshift. Now, dispersion measure is intrinsic to the signals. I understand how you measure that. How do you measure the redshift of these events?
That's a very good question. So DM comes for free from the radio measurement. You get the DM, and in order to measure redshift, you need to localize the FRBs. So early on, the radio beam is too wide; you cannot. However, when we start to see the repeaters, we know where it is repeating. Then you can have baseline many radio telescopes and the interferometer. You can narrow down it very quickly. So for all the repeaters, we can localize them very precisely. And now CHIME, and there are many more radio arrays, they start to detect, whenever they detect FRB, they localize them to arcseconds. So I just came back from the FRB 2026 meeting, the so-called CHIME outrigger, they already localized another 50 of them. And in Caltech, they have DSL, they localize about 100 of them. So this will be a major game changer. In the next few years, we should be able to localize maybe thousands or even 10,000 FRBs.
Let me just ask a short question. As far as I know, FRBs don't have optical emission, but magnetars do. Is that simply a question of sensitivity, or how do you see that?
FRB
FRB don't have optical emission, but magnetars do have optical emission. So is that only a question of sensitivity, or that we are less sensitive because, you know, FRB are very far away?
FRBs definitely, magnetars, the X-ray, including the X-ray burst. X-ray burst is about 4 times in magnitude in terms of luminosity and 5 times in energy. But those bursts, if you put a cosmological distance, just cannot be detected. Imagine that what we detect are GRVs. They're 10 orders magnitude brighter. So 5 orders magnitude is still not easy. Yeah.
Okay, short questions. Burst duration is milliseconds. And what about the interval period repeater?
Yeah.
One. And then let me finish. Then the other thing I like to know is a coherence, length, time, length and time scale. Coherence. When you talk of cohesion, you
okay. The first is the interval separation. It depends on which source and depends on sensitivity. So with CHIME, because it's less sensitive, they usually detect it maybe once a few days or something like that. But with FAST, because much more sensitive, when we start to observe some of the active repeaters, we can detect the 700 per hour. That's a lot. 700 per hour. 700 bursts per hour, which means that they're very, very close to each other. So those bursts.
How much? Between 100 times larger than duration?
So each one is millisecond.
Yes.
Within one hour, you detect 700 of them. So you can calculate how many. So it's typically seconds. You start to pick up the next one.
Hours.
Yeah. That's very active ones. And some of them, they're just not active. So some of them we followed for 2 hours, nothing was detected. So these things are very strange. And even for active repeaters, sometimes they are very active, and a few days later, suddenly it disappeared. So we can no longer detect it. The second question about coherent length, it is just wavelength of the emission. It's 30 centimeters. So we need that within the 30 centimeter, we have the particle charges to radiate coherently. Yeah.
Yeah, thanks for the nice talk. So I had just one clarifying question. So you mentioned that when FRBs are repeating, they could be magnetar in binary with aligned magnetic and rotation axis. But if I understand correctly, if the magnetic and rotation axis are aligned, then there's no pulsar emission. So is it the binary companion which is then driving the pair production or whatever process in the magnetosphere?
That's a very good question. So the triggering mechanism FRBs, we actually don't know. So it cannot be simply just the spin down because the luminosity is so high. So what people speculate is earthquakes. So the magnetar is continually quaking. So for every say quake, you send out some alpha waves and faster magnetic sound waves and particles, and you do that. Then the question is, why in the binary systems you have more such kind of triggers? Two possibilities. One is actually in other systems they also have these triggers, but because they are misaligned, some FRB just cannot get out. So that is one interpretation. Another interpretation, more extreme, is that this companion is helping to trigger this, but the energetic wise, is not large enough. The wind from the companion when reaching the magnetar, the energy is not enough to trigger, to really power a FRB. But you can in principle send some alpha waves into the magnetosphere and trigger some instability inside. So that is a speculation. So there is a possible way that you can use the companion to power more FRBs.
Thanks.
Thanks for the question. Just short one regarding the rates. So knowing that galactic magnetas is 30 or so, and having that observed magnetar related FRB, what is the rate then and how it is changed giving this observation?
Very good question. So in our Milky Way, we haven't detected any active repeater. So there are two possibilities. One is that these are all isolated magnetars, and we don't have a magnetar in the binary system. And another is beaming. So we work out the numbers. So according to our simulation, maybe 4% are in the binary system, 96% are in the isolated system. So it is still barely consistent. It might be a companion, and in that case, the beaming will start to play the role. So my speculation is maybe in our Milky Way we have active repeaters, but they're just beaming towards some other directions. Aliens from other galaxies will see an active repeater, but we cannot.
So you think that FRB as a tool can help us to detect more magnetas in our galaxy? Can or not?
You mean detect more magnetars from our Milky Way?
Yeah.
Yes. In principle, that is possible. But I should say that X-ray bursts are much easier to make than FRBs. For that particular FRB in our galaxy, we used fast to observe the source for many hours, and during which there are already about 100 X-ray bursts, but no radio emission. And suddenly something happened. So this is consistent with the picture I just showed. FRB is a much more narrowly beamed compared with X-ray emission. So maybe the best chance is we still detect new magnetars through X-ray bursts, and then we detect a radio burst. But I don't rule out the possibility that you'll find a radio burst first. Yeah.
Okay, thank you.
Let's go for coffee break and the next sessions.
Yeah, thank you. And Dili actually texted me. He's at the Shanghai airport, and he doesn't want to delay too much. So maybe we can let him to speak soon.
What happened?
Dili is next speaker, right?
Yes.
He's supposed to start at 11.
Yes.
And he is sitting at Shanghai airport. If it delayed too much, he couldn't finish his talk. I think that.
Talk now. Maybe it's going to
Yeah,
right now.
yeah. Let him talk now.
Then we break for a okay.
Yeah.
Let's do that.
Yeah. Okay.
I want to apologize first that I cannot make it to the meeting, but I'd like to share with you some of the recent progress in studying in the uh, radio study of the neutron stars. So there's this general line of development of human cosmology. So with the start with rather complex model with 20 some IP cycles, and later Kepler actually tried to explain planetary orbits with platonic solid. So only with start with Galileo's usage of telescopes that give birth to the modern cosmology. So there's this sort of cycle of model observation and refine it with physics. So most of the information from the cosmos come in EM band, and in the later half of the 19th century, Heinrich Hertz managed to demonstrate the propagation of EM waves. And in the process, he actually invented the first antenna that is sort of make feasible all the subsequent radio astronomy. So that's the same technology that's in our phones and in the whole communication industry. So the main focus and achievement of the early half of the 20th century astrophysics, predominantly in stellar astrophysics. So after the proposal of the electron degeneracy pressure along those giant nucleus hypothesis, immediately after that, nowadays astronomers generally credit the invention of the term or invention of the concept of both supernova and neutron star to waterbed and freeze Vicky. They have this start with this very brief note on PNAS titled Remarks on Supernovae and the Cosmic Rays. They start to discuss this at the time sometimes called a giant nova. Its occurrence in the Milky Way. They are off by one order of magnitude, but no matter. Toward the end of this brief note, they expect or hypothesis that such giant explosion should result in a neutron star. But we sort of have to wait for another 3 decades and a world war to see the observables from the result of that giant explosion. Dawson Bio and Hurish detected the first batch of pulsars, and immediately after their discovery in 1967, the pulsar in the supernova remnant, that is the Crab Nebula, was detected with a spin period of 33 milliseconds. So only a few months after that, Thomas Gold of Cornell University started to draw up this lighthouse model that explained the power of the radio emission with the spin down of the neutron star, which was quickly borne out by the observed period derivative of the Crab pulsar. So this realization and observation of bright radio pulses from compact object spurred immediately search for such cosmic radio pulses from even larger distances. So this is the earliest search of the so-called fast radio bursts I can find in the literature. Is actually from 1978. Dr. Peter led the team. They tried to search for a giant pulse from a supernova within 100 megaparsec with a isotropic energy of 5 times 10 to the 30 ergs. So all their numbers and concepts are exactly correct. They just don't have the right fortune or technology at the time. So the application of Hertz's invention of radio antennas start to be used to astronomy applications. Start with Karl Jansky and Grote Reber in 1930s, but their work were largely ignored by astronomers who were busy with stellar astrophysics and building atomic bombs at the time. Only after World War II, a graduate student in Harvard physics, Harold Urban, with his handmade, very rough sort of invention of the antenna, detect the hyperfine structure transition of the atomic hydrogen in 1951. So only that major discovery spurred the growth of radio astronomy as a subfield of astrophysics. And that quickly lead to a US ambitious project that established Arecibo toward the end of 1963. This 300-meter diameter antenna is a technical wonder of the 20th century and stay on the apex of sort of man-made antenna for a little more than half a century, which is quite amazing. So it was initiated by Bill Gordon from Cornell, and its discovery of the first double neutron star won the Nobel Prize in Physics in 1993. So following that, Chinese astronomers, particularly Dr. Ren Dongnan from Chinese Academy of Sciences, start to push for a bigger giant antenna sitting on the ground. Initially, actually, as a precursor concept for the square kilometer array since the early 1990s, and it finally got built and operated since early 2020. So I think it will have a deep impact and a long influence for the 21st century astronomy. So this search for more distance cosmic burst, a radio burst, finally succeeded in 2007 with the detection of the first fast radio burst at the time was referred to as the Lorimer burst. And only in 2017, the first repeating fast radio burst was localized to a metal core dwarf galaxy at a redshift of 0.17. And this repeating fast radio burst was discovered by the Arecibo telescope, and it was the last major contribution from this great observatory. So the localization and thus the confirmation of a cosmic logical origin of fast radio bursts was dubbed the most important discovery in astronomy since LIGO by American Astronomical Society. So with the independently measured distances, we can roughly estimate that in 1,000th of a second, a fast radio burst can emit as much energy as a full year's worth of solar radiation. So by that time, all the money for the FAST project has been spent, and we really have to think of how to accomplish all the set goals of the FAST observatory, namely and primarily the mapping of the hydrogen line and the systematic search of pulsars, but also try to dive into this new field of fast radio bursts. So from 2015, we started to test out this new mode, which we increase the injection of the electronic calibration signal frequency from roughly about 1 Hertz to 10,000 Hertz. Thus, we leave a clean enough part of the power spectrum of the time series that we can leave this Cal signal on while search for pulsars and get calibrated H1 imaging data. This has never been accomplished before. For example, at Arecibo or at Parkes or any other major radio observatory before FAST, people always have to do a H1 survey and then do a pulsar survey, then do a H1 galaxy survey separately. So the invention of this high cadence Cal technique, which give birth to the so-called commensal radio astronomy fast survey or CRAFS mode, multiply the survey efficiency of such a large single dish observatory. By now, the CRAFS survey covered about 30% of all sky visible to FAST. And the CRAFT survey has resulted in more than 220 new pulsars, including the first new discovery from the observatory, about 60 millisecond pulsars, 3 new double neutron stars, and all the confirmed discovery and published pulsars. The original data and the subsequent information are all publicly available. So the H1 imaging is also working well. It just took much longer to get it properly processed and calibrated. So this is a combined H1 image of the Andromeda galaxy. That's the fast H1 image combined with the VLA archival image that result in the best quality H1 image of any giant spiral galaxies. So with this data set, we manage in the channel map to find out more than 100 super bubbles, and these super bubbles require somewhere between a couple to a dozen supernovae explosions. And then we plotted the energy, expected energy injection rate against the derived turbulence dissipation rate, and they match each other really well at every galactic centric distances. So I think this is the first direct evidence that in the giant spiral galaxy, star formation, particularly supernova explosion alone, are capable of driving all the turbulence there. So while we are searching for pulsars and mapping the hydrogen, the CRAFS mode also almost in real time try to search for giant pulses from beyond the Milky Way. So on May 20th, 2019, our postdoc at the time, Dr. Chenghui Lu, noticed that there are multiple bursts with excessive dispersion measure in different feed horns of our multi-beam receiver array. And then it took us about 3 years to get properly localized and get the X-ray and optical data. And it was now confirmed to be a very active repeater from another metal poor dwarf galaxy, roughly at the redshift of 0.24. And it's still the first of its kind in that it's so-called persistently active. So ever since its discovery in 2019, every time we turn off a telescope at the source, it always managed to produce at least 2 bursts. So this is an ideal target to be followed up. So this is a summary graph of all the published more than 3,000 fast radio bursts. You can see it's dominated by those white dots. Those are the discoveries from the very successful Canadian CHIME experiment. And the other symbols, particularly rise stars, represent discovery from the FAST observatory, particularly the CRAFT survey. It's only we only discovered 10 new fast radio bursts from CRAFT, including the repeater I just mentioned. It's nowhere even close to CHIME's discovery rate, but they are in a relatively clean part of this graph, which is at higher redshift and tend to add lower flux. And from this relatively unbiased sample, we can backtrack out a fast radio burst event rate at more than 120,000 full sky event rates every day. So I fully expect that this observation confirmed date will further increase with the advent of square kilometer array. It's probably somewhere between 1 million to a few million detectable radio bursts from outside of the galaxy every day. And after the discovery of 1905-20, the first persistently active fast radio burst, we were also able to catch a very active episode of the Arecibo discovered first repeater, the so-called 1211-02. So between the end of August of 2019 to middle October, in 50 days, we detect 1,652 bursts, and this data set enable us to get the first complete energy spectrum of any fast radio burst, and it has this bimodal shape. In the lower energy part, it's well fitted by a log normal function, which tend to represent some stochastic process. And at higher energy part is a Lorentz-Cauchy function, which may be two coincidentally correlated random events. So that start to give us some physical constraint of such radio explosions. Subsequently, FAST has been able to catch many bursts from a small set of active repeaters, and this bimodal or multimodal shape seems to be common. I think it's also worth noting that the characteristic energy transition from this lower energy bump to this higher energy component tend to happen within one deck of energy, which is between 10 to the 37 to 10 to the 38 ergs. And if we can further correlate such behavior to the, for example, the characteristics of its environment, I think it even has some remote hope of becoming a standard candidate. So the observational study of such phenomenon in terms of number of detections is roughly, so everything starts at parks from 0 to 100, and then CHIME come into play, bring this number from 100 to a few thousand and keep on increasing. Then FAST focus on few very active repeaters, so bring the total number of detections into tens of thousands regime. And in 2023, the discovery of fast radio bursts were awarded Shore Prize. And in 2024, the work done at Chime as well as FAST were awarded the Marcel Grossman Award. So now we have a rather rich set of observations, and it become a cottage industry of trying to find some systematic trend to discern the repeating fast radio bursts and those a majority single bursts. For example, in the recent release Chime catalog, only 3% of the fast radio bursts were seen to repeat. But there doesn't seem to be any conclusive evidence so far. For example, last week, Bing Zhang, Wei Wei Zhu, and I organized this annual fast radio burst conference in Guizhou, where the fast is located. And there is an unofficial poll of the attendees, and roughly 50% of the attendees think, oh, fast radio bursts repeat, and the other half of the experts think they are of two distinct class. The alternative to such division may be that they are of a single class, but they reflect this class of sources at different ages, right? For example, when they were born, they're very active, so you have a higher chance of seeing them repeat, and then it become less and less so. In fact, it's common in astronomy to sort of use the evolution in time to try to accommodate the diversity of the observed phenomena, because for most of the phenomena, we're basically getting a slice of time of the cosmos. Fred Hoyle was very smart, so he actually predicted the triple alpha process with resonance energy at around 7.77 MeV, which in turn help complete the CNO cycle picture. So now, for example, we know that the sun can start off on the main sequence and eventually become a red giant. Recently, we start to also discover new class of neutron stars in radio. For example, this is a combined a composite image of X-ray in blue and the meerkat radio continuum in red. So at the center, there's this so-called central compact object that is very active in radio, but for the past 20 years or so, there have been no, very active in X-ray, but there have been no radio counterpart being detected toward any of the CCOs. So we were able to use the meerkat, a South African square kilometer array precursor, to detect the first radio pulse from this CCO. And just given its look, we dubbed it a blinking blue eye. So this was just published on Nature Astronomy a couple of weeks ago. So this is also one of the few sources that has X-ray absorption, and it's very likely come from electron Landau energy levels. So now we have this rare case that we can combine X-ray absorption with radio emission to further constrain its magnetic field. It turns out that the CCOs are confirmed to have a magnetic field 1 to 2 orders of magnitude lower than most of the normal pulsars, but still able to produce very strong coherent emissions. We have another recent paper that we, through the fast cadence imaging, we detect a long period transient of 44 minutes periodicity, very likely to be associated with a supernova remnant. So this class of object, so-called LPT, there are only 2 LPT that have confirmed origin. So those are white dwarfs in binaries. So for isolated long period transient, you have to explain somehow. For example, if it's white dwarf, you have to stir up its magnetic field. If it's a neutron star, you have to somehow slow it down because if it allow it to be rotationally powered for such a long time and evolve from seconds to like hour, then the presumably the magnetic field strength will be too low. So our proposed story is that it's the supernova fallback breaking. So you can see on the graph on the right, this is a circular array of 313 antennas, each of 6 meter diameter. So it was designed originally to look at the sun. So this is the first nighttime discovery of the so-called dark array. I think it's also demonstrates that the supernova is generating more diverse class of objects than we previously know. So at the time of the discovery of 1905-20, it also shown that when the fast radio burst is not on, we can still see the source as a so-called persistent radio source. So it looked very much like a supernova remnant. It's just very bright. 1905-20 was only the second fast radio burst with a PRS counterpart, the first being FRB 121102, the first known repeater. So this class of object now start to show some unifying behavior. So this is a paper led by Yifeng, published in 2022. So we noticed this unified behavior that if you measure this the polarization of the burst from a certain source, it tend to trending toward 100% linear polarization toward higher frequency. Then it dropped like a stone and eventually go to 0%. And this is well characterized by the complexity in the magnetized plasma through so-called multipath scattering. So if the dropping frequency, characteristic frequency is higher, it means the plasma is more complex. And presumably, I think it also means the source are younger. So the two youngest source, at least at the time, are actually the two sources with persistent radio source counterpart. So only this year, we start to be able to see a clear evidence of the long-term evolution of fast radio burst sources, particularly the dropping of its dispersion measure, which presumably come from the expansion of the supernova bubble. For example, 121102 is dropped roughly 4 every year, and 1905-20, which was published earlier this year, dropped about 12 every year. So I think this is the first batch of clear evidence that the fast radio bursts, at least the active ones, originate out of supernova explosions. So this is a model that we're still building. So looking in the collection of radio observation, we only have a single evidence of dispersion measure evolution from a supernova remnant, which is a Crab pulsar. Right? So because we know the Crab pulsar, the associated supernova happened in 1054, roughly 1,000 years ago. And in the past half a century, the dispersion measure of the Crab pulsar dropped by a unit of 0.1. So roughly a few hundredths of the decreasing rate of dispersion measure of 1905-20 and 121102. And from here, we can actually backtrack out of the initial conditions of the two supernova that produced 121102 and 1905-20 and its age. So it both of its age has to be somewhere between year 10 to year 100, because it cannot be too young. Otherwise, the plasma is still opaque. It also cannot be too old. Otherwise, you start to hit this so-called snow plowing side of Taylor phase. The dispersion rate dropping will become almost imperceptible. So I think we're very close to solve the at least the astronomical origin of fast radio bursts, and through the observation of such extreme transient phenomena, particularly in radio, since we fully sample the phase and magnitude of radio wave, we get based on the Shannon theorem of the information theory, we will get full information of any transient phenomenon in the radio band in the cosmos. And this information content are also tied to the energy range through the uncertainty principle, which in turn, eventually, I think we should be able to prove a direct logical link between the Planck constant and the age of the universe, because the finiteness of the universe is what gives rise to the quantum characteristics of the universe. So I'm coming to the end of my talk. I think all fast radio bursts originate out of supernovae, and they evolve. And fast radio bursts are associated with a peculiar class of compact stellar population, and they tend to be born in the metal poor environment. And the prediction, which is falsifiable, is that all the early stage active repeaters with persistent radio source counterpart, we should start to see their dispersion matter dropping year by year. But the final proof would be we should be able to see a supernova after some time to allow the plasma to dissipate and start to see a active fast radio burst repeater. And so when I gave this talk in Hong Kong, Brian Schmidt told me that humans' coverage of supernova are not complete for anything within redshift of 0.1. So I hope or fully expect that we'll be able to see such a sort of clear link of the supernova to fast radio bursts within the next 5 to 10 years. Thank you. Hello?
We heard this morning by Big Zhang is a fantastic continuation, and we look forward to continue in the next meeting in Beijing in September, October, and prepare for the Grossman meeting next year in Hong Kong. Let's see if there is any question, urgent question by any one of you. Maybe Roland, you can find exciting this also this topic, although it's premature, but it looks is going to observable very fast. Any question?
No question. Then now we can go for coffee break.
laboratory to test relativistic gravity and in particular general relativity. So let me go on. So as you know, GR has passed many different tests throughout. Apologies, I think the Zoom link opened on myself. So I was saying, as you can see from this graphic, from this little plot with the parameter space of gravitational potential and space-time curvature, that GR has passed many different tests in many covering large areas with different probes. And on the top part here, with higher space-time curvatures, so that we have, and some very peculiar ones are linked to pulsar observation. And the high precision, the very high precision that we can reach with these tests through pulsar observations are due to the fact that pulsars, which are these, as you know, highly magnetized, fast rotating radio lighthouses in the sky, are, especially the fastest rotating ones, the millisecond pulsar, are extremely precise clocks. So by looking at how these clocks fall into the space, into the curved space-time, we can get very precise tests of relativistic gravity. And this is we predict times of arrival on the basis of a pulsar model. When we discover a pulsar, we can have its rough position, rough spin period, and after a while we can get some information on its orbit. So on the basis of this initial model, we can predict times of arrival. Then we measure times of arrival of our pulsar with repeated observation over different timescales, depending on what parameters we are interested in measuring. And by comparing predicted and measured times of arrival, we can create the so-called timing residuals, just the difference between the two. And the timing residual will show different trends accounting for the miscalculated parameters in our rough initial model. So by fitting for model parameters, we can remove trends from our timing residuals, and the final aim is to recover something like this. So these are timing residuals on the x-axis. You see the scale is something like 2 × 10⁻⁷ seconds, so it's very precisely measured, versus the date. These are MJD on the x-axis. And yet the final aim is to get flat timing residuals with a small RMS around the zero without any specific trends. And once we get this, this means that the model that we're using to reproduce times of arrival, to predict times of arrival, is correct. And we can recover pulsar parameters with very, very high precision, as you can see in this little inset here, where, for instance, you can see that the spin period of the pulsar is known with a precision that is attoseconds, or the semi-major axis, this A1 parameters, is known with a precision of nanometers. So it's incredibly precise measurements that we can get for our pulsar and our binary system. In some cases, however, for some binary pulsars, the accuracy of the measurements of our times of arrival is so high that if we only use the Keplerian description of the orbit, so the 5 Keplerian parameters of the orbit, we cannot obtain flat timing residuals. We still see some trends over orbital timescales or over longer timescales, which means that, that the Newtonian description of the orbit is not sufficient to describe the system, so we need to plug in additional physics, which we can test through our pulsar timing method. And of course, the additional physics that we want to test in this case is relativistic gravity, and in particular GR. So a successful framework for testing a large class of gravity theories is that of the post-Keplerian formalism introduced by Damour and Deruel in 1986. And in timing, the post-Keplerian parameters introduced are operationally defined. They basically don't assume the validity of the chosen theory of gravity. So for GR, the five main post-Keplerian parameters, as you might know, are the periastron precession, describing the fact that the orbit is dot closed, the two parameters R and S, rate and shape of the Shapiro delay, describing the extra path that our pulse, radio pulse from the pulsar has to travel across due to the curvature of the space-time introduced by the companion star. We have the gamma, gravitational redshift and time dilation parameters in the orbit. And finally, the PB dot, the orbital decay, which describes the shrinkage of the orbit in time due to loss of energy by emission of gravitational waves. So measuring PB dot means testing the existence of gravitational waves. So in any chosen theory of gravity, the post-Keplerian parameters take a different functional form. These five here are for GR, and they can be written, even though the functional form is different, for any theory of gravity, they can be written only as a function of the Keplerian orbital parameters, which are known with very high accuracy from the pulsar timing, as I showed you before. And the only unknowns here are the masses of the pulsar and of the companion star. So 5 equation, 2 unknowns. So if we measure any two post-Keplerian parameters, we get we define completely the system. We get the masses of the pulsar and of the companion. Capital M is the sum of the two. We can plug them into here, into the other two, to the other three equations, get a prediction for the post-Keplerian parameters, for the other three post-Keplerian parameters. And if we measure any other post-Keplerian parameter, we can get out with a test, a consistency test of this chosen theory of gravity. In the case of this 5 equation approximated to the first order, it's of course GR. So we can do, by measuring n post-Keplerian parameters, we can do n-2 tests of the chosen theory of gravity. The same thing can be seen in a graphical way by putting all the constraints on the masses that we can get from these equations into a mass-mass diagram. We have the mass of the pulsar on the x-axis and the mass of the companion in the y-axis. The first constraint that we can put here is purely Keplerian, comes from the measurement of the Keplerian parameters and of the mass function of the system, where you see there is the sign of the inclination in the equation. And so by simply imposing that the sign of I has to be lower than 1, we can exclude all this gray part of the graphic just from Keplerian assumptions. If we measure 1 and then 2 post-Keplerian parameters, as I was saying, we solve the system, we get the masses out, and by measuring a third post-Keplerian parameters, if its curve crosses in the same point, or rather in the same area, since every measurement has its own error bar, with the other two curves, then the theory is working. Otherwise, we have to discard the theory. It's working within the errors. So this kind of test was done for the first time on the very first binary neutron star and binary pulsar to be discovered. It was this B1913 plus 16 pulsar, a 59 millisecond pulsar, orbiting in a 7.8 hours eccentric orbit around another neutron star. And after a few years of monitoring, 3 post-Keplerian parameters were measured from this system. Omega dot here in black, gamma in red, through which the masses were measured. And the third post-Keplerian parameter measure was the orbital decay, this blue curve here, which allowed to test relativistic gravity in particular. Have I dropped out? No, I'm still here. So I'm not sure that I'm still connected. I think so, I hope so. So this is the first test of relativistic gravity done through pulsars. And the proof of the existence of gravitational waves. Sorry, I'm not sure that I'm still connected, am I? I'm not sharing the screen anymore, for some reason. Sorry about that. I don't know what happened. Have I dropped out? No, I'm still here. So let me start sharing my screen again. Apologies. I don't understand what happened, so I should be back. Okay. So I think I dropped out while saying that this was the first proof of existence of gravitational waves, and that led to the Nobel Prize in 1993 in physics being awarded to Taylor and Halls, the discoverers of this amazing system. Some 10 years later, an even more amazing system was discovered. I was the lucky one to discover it in the course of my PhD thesis. This is the first and so far unique case of double pulsars. So both neutron stars in this system are seen shining as radio pulsars. The fastest one is so-called pulsar A. It has a spin period of 23 milliseconds, and it orbits a 2.7 second slower younger pulsar in a slightly eccentric orbit of only 2.4 hours, which means that the orbital velocity in this system is quite high, 0.001 c. And also, very interestingly, from the point of view of the possibility to measure precisely post-Keplerian parameters, the inclination of the system is very high. The system is basically seen edge on. The inclination is 89.35 degrees. So after only 1 year of observing this system every couple of weeks or every month, we were able to measure all 5 post-Keplerian parameters of the orbit that you can see here in this mass diagram. The orange part of this graphic is excluded by the mass function of pulsar A in the lower left corner, but also we have the mass function of pulsar B in the upper left corner and lower right corner. And besides the 5 post-Keplerian parameters, you can see here with their error bars, there's an extra curve, this R. This is the mass ratio between the masses of the 2 pulsars, which is uniquely measurable in this system because we do see both pulsars. So by the ratio of the masses is equal to the ratio of the projected semi-major axis. So this is a theory-independent constraint that we have on top of everything else here. If you zoom into this little area here in this little square, you see that all the curves for the different post-Keplerian parameters match in this one little point, telling you that GR is working very, very well for this system. But the beauty of timing observations, of timing measurements, is that the precision with which we measure the various parameters increases as we keep on observing, increases with time. So different post-Keplerian parameters increase their precision on different time scales, but all of them increase in time. So if this was the situation in 2004, look, for instance, at the black curves for PB dot, and look how they shrink. This is 2005, and this is the PP dot diagram that we publish in our most cited paper, Kramer et al. 2006, 20 years ago now, where you can see that we have now all 5 post-Keplerian parameters plus the mass ratio, so far 4 potential tests for GR, so more than in any other system. And the most precise test that we get is from the Shapiro delay measurement, through which we verify GR with a precision in just 2 years that is 4 times larger than what was achieved in the Nobel Prize pulsar in 20 years of observation. So this is an extremely fruitful system to test GR, as already 2 years of observation proved. But of course, we have now 20 more years of observations, and we took all of our data a few years ago and published them in a huge paper. It's a 50 pages paper, Kramer et al. 2021, collecting something like 1 million times of arrival collected from all the major radio telescope that could see the double pulsar in the world. And with this work, we achieved a precision that is higher than ever in the measurements of the times of arrival, and therefore on all the parameters that depend on them. And the consequences of this incredibly high precision is that, well, first of all, the tests of GR that we can do are the most precise ever. So these two plots are the plots for the shrinkage of the orbit, of the orbital decay for the Nobel Prize pulsar. The current tests with the measurements of PB dot for this pulsar is at this level of precision. The current test for the double pulsar is more than 10 times more precise than the Halsen-Taylor pulsar. And the impressive thing is that the measurement that we've done, which is basically that the orbit is shrinking by 7 millimeters a day, implying that the two pulsars will merge in about 85 million years, is so precise that now, to account for its precision, we have to take into account the relativistic mass loss in the system, so E equal to mc squared, right? So the pulsar is emitting electromagnetic waves, radio pulses, so it's losing energy, rotational energy through that, and so it's also losing mass. It has a relativistic mass loss, which is of the order of 10 to the 21 masses of pulsar A per second. So, it's tiny in a way, but our precision, our measurement are so precise that we do need to take that into account now. So I think it's quite amazing. So the second consequence of this very high precision is that now we need to expand our equation beyond the first order. And this is true, for instance, for the measurement of the periastron advance omega dot that you see here. These in parentheses are the errors on the last quoted digit. So we have, since we have now observed it precessing over more than 360 degrees, our measurement is very, very precise. It's on the 5th or 6th decimal digit, and the 2pn contribution enters at the 35 sigma level. It's of the order of, as you can see here, 10 to the minus 4 degrees per year. So we do need to take this into account. And at the same order, around 10 to the 4 degrees per year, enters another effect that I will talk about towards the end of my talk. So put a pin in here and remember it for later on. But the consequence of the need to take into account the second most Newtonian order and these extra parameters is that we now are starting to be able to measure the moment of inertia of this neutron star. I'll get back to this towards the end. So the third consequence of our very high precision is that we are now able also to measure higher order light propagation effects. So the first order light propagation effect that I was mentioning before is the Shapiro delay, which, thanks to the fact that this system is seen basically edge on, is very pronounced. So the pulsar, the beam of pulsar A, the millisecond pulsar, when it points towards us at conjunction, passes only 10,000 kilometers from pulsar B, from the slower rotating pulsar here, which means that the Shapiro delay is higher, is very high and very pronounced. And this is what we see in this plot here, where the red curve is the prediction from GR, and the blue points are our measurements with tiny, tiny, tiny error bars. And this provides us with two tests for relativistic graph for general relativity, quite precise, not as precise as the PB dot test, but still 2 extra tests. But if we zoom into here and we subtract the first order GR prediction from the Shapiro delay, we actually see that there are a little residuals, meaning that before superior conjunction, the pulses are arriving a little late, and after superior conjunction, the pulses are arriving a little early. And why is that? Well, this is related to this higher order light propagation effect that I was mentioning. The first is retardation effect. So the orbit of our pulsar is some 3 light seconds across. So by the time the pulse from pulsar A reaches pulsar B has moved in its orbital point, which means that the effect of the Shapiro delay is slightly shifted, as you can see from this graphic. So the blue curves what we would expect if the light propagation was like instantaneous, but since it's not, the effect is slightly shifted towards slightly earlier orbital phases. And thanks to the precision of our measurement, this is the first time that we can actually see these. On top of this effect, there is a second effect going in the same direction, so summing in phase with it, which is related to light bending, so light deflection. So the pulses of pulsar A gets bent by pulsar B at superior conjunction, making them arrive a little later than predicted before superior conjunction and a little early after. And because they arrive a little later and a little early and not the other way around, this means that the rotation of pulsar A has to be prograde with respect to the orbital motion. So thanks to this extremely high precision, not only we can measure these 2 higher order light propagation effects for the first time, but we are also able to determine that the sense of rotation of pulsar A, which is again something quite amazing if I say so myself. And fourth and last consequence of our very high timing precision is that now we are also able to measure a new post-Capellian parameters, the relativistic deformation of the orbit, which is predicted by GR. So in this little animation, it is enhanced by something like 1 million times just for display purposes. And the net effect is that the elliptical orbit is slightly deforming into a like sort of egg-shaped shape. And we don't measure these parameters very well right now. We have a slightly higher than 1 sigma detection, 1.45 sigma detection. But if we do not take this into account, we are in trouble with another relativistic parameters, gamma, with which it covaries. So we do need to take delta theta, this deformation of the orbit, into account in order for gamma to match our prediction. So we have a constraint, although not very precise, also on these extra parameters that we do have to take into account. So to put it all together, we have, with this amazing double pulsar system, we have now measured 7 post-Capellian parameters, including this blue poorly constrained stripe that I will mention briefly, but I don't unfortunately have time to go through. 7 post-Capellian parameters plus the mass ratio. This is the latest mass diagram that we published in this Kramer et al. 2021 paper. This is the zoom in. For some of these measurements, for some of these parameters, we now need to add to go to next to lead in order signal approximations, and we measure next to lead in order in signal effects in signal propagation for the first time. We have, as I was mentioning, the most precise strong field test of GR with a precision of almost 99.9 precision, and our precision is so high we now need to take mass loss into account, which is quite impressive. And as I was mentioning before, where I asked you to put the pin in that slide where I was talking about the per-astron precession omega dot, we now are able to start to probe the moment of inertia of neutron star, and therefore to constrain equation of state of neutron star through timing measurements. And this is because at the same level of the second post-Newtonian order, there is another effect affecting omega dot, the measurement of omega dot, which was predicted already in 1988 by Damour and Schaefer, which is a frame dragging effect, lens steering effect on pulsar A. And interestingly, in the equation of this omega dot, which you see it's of the same order, 10 to the minus 4, so it enters at some 30 sigma level in our measurements. It depends on IA, which is the moment of inertia of pulsar A. So if you zoom into the top, the zoomed version of the center of this graphic, what you see is that without taking into account these extra terms, these omega LT, our omega dot would be this dashed curve, while what we measure is this solid curve. And the gray area is where it is determined by the different moment of inertia that we can plug into here, covering from the radii allowed by causality limit up to 15 kilometers or something like less than 20 kilometers. So this gray area is related to the moment of inertia. So far, we are not able to put a very tight constraint on it because of the error bars of the other parameters. So you see here the purple one, the violet one is the error bars of the shape of the Shapiro delay. This pink one is the error bar of the measurement of PB dot, the orbital shrinkage, and the yellow one is gamma, which is quite larger. And as you can see, the crossing of the three more precise ones is not particularly constraining the gray area yet. But as soon as we will, since we will continue to observe this pulsar, these error bars will shrink, and we will be able, in the next 5 years or so, to constrain much better the moment of inertia, this little gray area. And for now, what we can do with the current measurements that we have is to put this constraint on the moment of inertia. It's not terribly good. I think it corresponds to a limit on the Newton star radius of about 22 kilometers. These black points here are from X-ray observations from NICER and from gravitational waves. As you can see, currently they are doing better than what we can do, but in a few years we should be able to push our limit in the same area of these other measurements. So constrain the moment of inertia and therefore the equations of state of Newton star nuclear matter with the double pulsar with a very accurate measurements. Last thing, these extra parameter that we measure with not as much accuracy of the other. It will take another like 10 minutes, so I don't have that time. But this is related to another relativistic effect, the relativistic spin precession that was predicted for pulsars by Damour and Ruffini back in 1974, basically immediately after the discovery of the Hall and Taylor pulsar. I think the Damour and Ruffini paper came out even before the Hall and Taylor pulsar paper was out. So they predicted that there should be this relativistic spin precession of the rotational axis of the pulsar, and this is something that we do see in our system, in the slowly rotating pulsar of our system, pulsar B, that in fact has precessed outside of our line of sight already in 2008. So we do not see pulsar B anymore in our double pulsar. The prediction is that it should reappear as soon as 2034, depending on the shape of the radio beam. So we are still monitoring our pulsars, both to put more and more stringent constraints on GR and on alternative theories, to measure the moment of inertia, and also to catch when pulsar B is coming back. So while we wait for the pulsar to come back, we are keeping on observing. The main instrument, one of the main instruments that we are now using to do our most precise observation is the Meerkat telescope. It's this 64 dishes telescope in South Africa, which will be part of the SKA mid radio telescope that will start operation 5 to 10 years, hopefully. And already with the first 2-3 years of observation with Meerkat, with the 64 dishes of Meerkat, we were able to reach timing precision which are 2-3 times better than what we achieved in 16 years of observing the double pulsar with the other experiments. And in these couple of years, we were able to see the higher order light propagation effects that it took 16 years to see with the other telescopes. So the future is very, very promising for observation of this pulsar in particular, but of pulsars in general, and radio astronomy in general, thanks to the advent of the SKAO radio telescope in the near future. So I stop here. I thank you for your attention, and I'm ready to answer any question that you might have.
We are far behind the schedule for just one question.
Well, this is a lesson for everyone. This is one of the most impressive work ever done on the relation of gravitational wave emission and the physics of the source in great detail in this feedback. I think everybody will enjoy in playing back the presentation and congratulate the SKA, especially the Cagliari Observatory, but also the splendid work of the SK collaboration, and look forward to 2034 to see the pulse, one of the pulsar reappear.
Thank you, Remo. Yeah, let's hope so.
Just one question.
I have a question about, is it possible that in the near future you will get some evidence on quantum gravitational effects in your data?
Oh, quantum gravitational effects.
The Shapiro effect.
Yeah.
The Shapiro delay is also applicable for gravitons.
Okay, I see. I don't know exactly for quantum, but I know that we have been using the double pulsar to test alternative theories of gravity. We have discarded some extreme Mondian theories, and we are able, I mean, changing the framework, changing those set of equation for the post-Keplerian parameters for your chosen theory of gravity. You can plot the mass diagrams. I might have, sorry, no, it's going to take a while. You can produce these mass diagrams for other theories and discard them or confirm them within the limits. Sorry, this was about, no, I have too many. But yeah, I'm sorry, I don't have a precise answer for quantum. I don't know where we stand in that, but I'm sure that same things that we can do with some of the alternative theories of gravities, like the Damures-Posito-Ferez and the Teves, we can apply to quantum. It would be interesting to know what sort of difference you would expect in the Shapiro delay in these cases.
Thank you very much. Let's going fast to the next speaker.
Thank you.
Okay, Zvi, can you hear us?
Yes, I can hear you very
Okay,
well.
please
I hope you
proceed,
can
share
hear
your
me.
screen and you can start.
Good afternoon. I'm trying to share my screen. I need some permission. Okay, I think I can try now. Do you see my screen?
Yes, we see.
Okay, perfect. So, good afternoon, everyone. I'm sorry I cannot be there. Some medical problem, but it is over, but I still have to rest. And I want to begin by remarking that Yakov Zeldovich was one of my heroes. I still have always Zeldovich and Razor on my book, on my desktop. Unfortunately, I never met him, But a friend told me that he once came early to a conference. In the evening before the conference, he was sitting in a bar and started talking with some guy for the whole evening. It was very lovely chat. At the end of the evening, he asked, "Oh, I forgot to introduce ourselves. What's your name?" And the other guy said, "Zeldovich." So my friend is surprised, "Zeldovich?" And the answer is, "Why not?" So I'm grateful that there is a conference in his memory, and I'm very grateful that I was invited to talk. My title is some sort strange. It says an unorthodox concordance picture of tidal disruption events. So there is sort of contradiction, because if it's concordance, how can it be unorthodox? I'll try to explain in the talk how this could happen. And all this work could not be done without the help of my collaborator. Leon Chan is a student at Colorado. Nimrod is a student in Jerusalem. Chio Chan was a postdoc in Jerusalem, and the rest are faculty members now, Julian, Tao, and Tatsuya. So I will talk about tidal disruption events. So this is the tidal disruption. This is the disruption moment. And more or less everybody agrees about this picture. This is from a simulation by Tao Ryu and Tal. You see the star coming, it is stretched, squeezed, and then disrupted. And when we see here the debris going out to large distance in this classical shape. So this is the initial phase, the star is coming in. Now, the classical picture was outlined in Martin Rees in '88. He pointed out that about half of the mass is bound, that it will go back to the vicinity of the black hole. The other half escapes, and it will go to infinity. The returning mass has a critical radius of a distance of about 1,000 Rg, and it is around this critical radius that the mass begins to turn back and go back and come towards the black hole. So this is a very important number, and this trip around takes about 1 month. Another important factor is that the tidal radius is about 25 Rg. This is the typical tidal radius for a star. So this is fairly close, fairly relativistic. This is basically what one can say almost Newtonian. So this is the classical picture. And on top of this, it was suggested that a compact disk form. And the compact disk is of the size of the tidal radius, which is about 25 Rgs. Now, what do you expect from such a disk? If you have such a compact disk, you expect a temperature of about 500,000 degrees, a few hundred electron volts, size of about 25 Rg. Typical velocity should be about 50,000 kilometers per second, 0.1 c. And the total energy emitted should be 10 to the 53 ergs, which is about half a solar mass converted to energy with efficiency of about 10%. So this is what's the expectation from the classical picture. And indeed, a few candidates were observed in the 90s in the X-rays. However, then came the surprise when they began to see these guys in optical UV. And the dominant population now of tidal disruption events that we are aware of, about 100. This is an early picture of just about 20, but we have more than 100 now. They are dominantly having a prompt flare of about in the optical UV in the regions in quite galactic center, so it's not AGN activity. Time scale is about 1 month, and the time decay decrease is about t to the minus 5/3, but there are some fluctuations around. This is the classical expectation also, that we should get this number. Why is this surprising? Because this tells us that we have an inverse energy crisis. The usual concept of energy crisis is if you don't have enough energy. And if you don't have enough energy, there's a crisis, and the prices of fuel is going up, and it's difficult to find fuel and so on. But an inverse energy crisis is that you have too much energy and you don't see it. This is what is the situation here. We expect 10 to the 53 ergs, but we see only 10 to the 51 ergs. This is not the only surprise. This is the most major surprise because to me, energy is always the most important factor. But there are other surprises. The temperature is about order of 10 lower, factor of 10 lower, 50,000 degrees instead of 500,000. The typical emission size is about 500 Rg versus expected 25 Rg. We see lines spreading, and so we see the lines correspond to 5,000 kilometers per second versus 50,000. And as I said, the total energy that we see in the prompt phase is only 10 to the 51 erg. So 2 orders of magnitude too small. This is not the whole story. Just to circularize the matter, if you want to take half a solar mass and put it, which is almost unbound, and put it into a very small disk of 25 Rg, you have to dissipate 10 to the 52 ergs. This is the circularization energy required to take the streaming matter, put it into a small disk. But even this is not observed. Even this is 10 times too large. So what is going on? This is a simulation from which is more than 10 years ago, slightly not realistic conditions, but this is our first simulation on this with Shiokawa was the main author at the time. And you see the structure of the returning stream. You see something like a disk, but the size of the disk is about 500 Rg. It's not, there is no small disk here. So there is no small disk, there is a big cloud. And there are shocks in this big cloud, but the shocks are taking place here. These are where the shocks are taking place at large distance. And this suggests a completely alternative picture. And this picture, we called it the outer shocks. Another version is stream self-interaction or stream self-intersection. But you know, when you have a good idea, at first people say that it's impossible. Then they say, oh, yes, maybe. And then they say, oh, yes, but we said it first. And to say that we said it first, you have to invent a new name. So people invented now a new name for this idea, where they call it stream collisions. It's all the same idea. It's the matter which is going around the black hole, return to at a large distance, self-intersect here, at this place. This is from a numerical simulation, which I'll show in a second. The matter self-intersect here. And at this place of self-intersection, this is where the energy is dissipated. Now, if energy is dissipated here, we can get a very simple idea for the overall luminosity. And the idea for the overall luminosity is the following. The accretion rate, the mass accretion rate is of the order of stellar mass divided by 3 T naught. T naught is about 1 month. Stellar mass, we know what it is. A naught, we know what it is. It's about 1000 Rg. So we know that Gm over A naught is about 1 over 1000. And this gives immediately an estimate of the peak luminosity. And this is the peak luminosity which is produced here in this region, in the outer shocks, when the stream self-intersect with itself. So this is the idea. Energy dissipation at the outer shocks. If you look at it, the size is about 500. I said before 1000, but we're talking about orders of magnitude. It's about 500 Rg. The duration is 1 month. This is what was observed. The luminosity is about 10 to the 43 ergs per second. This is the typical luminosity to be seen. The temperature is about 30,000 degrees. Again, the same right ballpark. And the energy is only 10 to the 51 ergs. This is what we wanted. And finally, at this place, the corresponding velocities are only 5,000 kilometers per second. So at first look, everything agrees with this simple picture. And so this is the basic concept of the model. Now, I mentioned that the first simulation that I showed you was sort of unrealistic. It was so we got a lot of criticism because your conditions are not exactly what's happening. So we went back, and now we are having a real star, realistic star calculated by MESA, full GR. Full GR was already in the previous calculation, and we have the simulations with full GR and the realistic initial conditions. This is the black hole here, and you'll see what's happening. Oops, here. Yeah, you see the star passing near the black hole. It is disrupted, and then we go on a big screen here. We see this disrupted star. This is the debris. This side will go out, will escape to infinity. This side will come back and fall towards the black hole. So we get this structure of unbound material, bound material, and you see the bound material begin to reach the black hole. And now we'll go to the next slide, the next movie, which to see what's happened on the longer time scale. So we begin here on the longer time scale. You see the matter went around the black hole, no disk. This is the vicinity of the black hole. You see here an enlargement, no disk. Now we begin to see some material accumulating here, but it's a very small fraction. On the other hand, we see the matter self-interacting with itself here at large distance of about about 1000 RG in this simulation. And this goes on for about 2.7 T naught. At the time, this was the longest and the most realistic simulation, and it is still one of the most realistic simulations that were done so far. So what is the outcome? No disk, we have only a big cloud. And shocks here at large distance, just what we were suggesting. This is a side view of this large cloud. You see this, it's become thick. This is the final stage. You get a thick cloud with some enhancement on the equator, but you see a fairly thick cloud, and this emitting cloud is optically thick. So this is the result of the simulations, but people said, okay, this was your simulation, but others say something else. So what do other people say? And here comes the story about concordance picture. There are 4 different codes that did this exercise, 4 different calculations that did this exercise, using 4 different codes, different initial stars, different assumptions. We have full GRs, other don't have, for example, Steinberg and Stone have Paczynski-Witta potential, Price have SPH, we use Harm 3D, they use their own code, unique proprietary code. This is an APH. And then Oblomastov did with unrealistic initial conditions, very small black hole, but still full GRMHD and added magnetization. This is the end picture of all the simulations. And you see this large cloud which formed in all of them. And none of them actually produce a small disk. Even so, Steinberg and Stone claim that they see circularization. I don't see it here. So this is why I call it concordance picture. The matter does not reach the black hole. There is no small disk is not forming. And what you have is a formation of a thick cloud, less than 0.01 solar masses reach the vicinity of the black hole. This is on a short time scale, on the time of the prompt phase. Most of the matter will stay at large distance, and eventually, it will come back to the vicinity of the black hole. So, as I said, this allows us to get the immediate estimate of the luminosity. Now that we have a confirmation of this idea, we take that This is the mass input. This is the efficiency of converting of the gravitational energy. This is the gravitational energy. And the product gives us Erb's energy per second. And this is the luminosity. So how does this compare with simulation? So what we did here is we took this very simple model. It's basically a semi-analytic model. It's nothing more than a semi-analytic approximation that you can almost work out yourself from this assumption. There are some corrections that you have to take into account, taking into account that in some system light does not escape so quickly, and so on and so on. So in some cases you are limited by Eddington luminosity, but not by in all cases. And what you see here is on the x-axis the mass of the black hole, and the y-axis the peak luminosity. And stars and points here are observed points. I have to warn you that these points have very large error bars, definitely in the x direction, because there is a huge uncertainty of about factor of 10 in estimating black hole masses. These are black holes that we don't see directly. We see them in the tidal disruption event, but for this, we have to figure out how to recover from the tidal disruption parameters, the black hole parameters. In most cases, the black hole masses are observed from the galactic masses involved, and these estimates are uncertain up to a factor of 10. So you can imagine large error bars in this direction. Now we stop here at 10 to the 8 solar masses. We stop at 10 to the 8 solar masses because our model as it stands does not allow for more massive stars to produce tidal disruption event. This is a result that goes back already to Hills in the 70s, who was the first to propose a tidal disruption event. He pointed out that if the black hole is too massive, it will simply swallow the star before disrupting it. And this happens around 10 to the 8 solar masses. So our model does not suit for 10 to the 8 solar masses. There are observational claims of few events here at around 10 to the 8.5 and more than 10 to the 5 error per second here, which will be here on this figure. We didn't include them in this fit because simply either the black hole masses are wrong or something else. But in any case, we a priori say that after the 60 event in the sample, 5 clearly do not agree with this model, and they may be there as tidal disruption event, or they may be something else, but we don't try to fit them. If you don't try to fit them, you get this very nice fit, and we get this fit by assuming a dependence of a number of events on the black hole mass. And the result that we get, this is now a result, not something that we feed in, is that you need a constant rate of event per black hole mass. And we also have to feed in an initial mass function, and we get something which is not exactly, but very close to Krupa. So I said here approximately Krupa initial mass function, which declines slowly and then declines sharply above about 2 solar masses. And I want to stress that we obtained this fit without free parameters on the observations. This is without free parameters in the model. The model that I described here, sorry, I went in the wrong direction. Oops, something wrong here. The model that I described here basically does not have free parameters. It depends on the mass of the black hole, on the mass of the black hole, on the mass of the star and on T0 and A0, but T0 and A0 are simple function of M star and the mass of the black hole. So there are no free parameters in this game, and we still get this very nice fit. Okay, this is not the whole story. There were some interesting general relativistic effects so far. The calculation was included GR, but it's almost Newtonian. The most important relativistic effect is the upsidal precession. So if you have a star and the star comes on this trajectory, then this is the original trajectory if nothing would have happened, but the star is disrupted and it goes up along, the debris goes on such a trajectory. But now, if the encounter is very deep, let's say it's 10 gravitational radii instead of 25, then there will be upsidal deflection. And this upside deflection could be significant. And this means the following, that if this was the expected trajectory of the stream before, this will be the new trajectory. And this means that the self-intersecting shock that we discussed before will be here rather than there. This is nearer to the black hole, the gravitational potential is larger, so we expect these shocks to be much stronger, and we expect that something different will happen. So the question is, does this change the picture if we have a very deep encounter? So last year we set to solve this problem. This was done by Leon Chan, who is a student of Tao now in Colorado. And this is again fully relativistic simulation using hard 3D, initially realistic star, very close impact of the initial star. The initial star passes at 10 RG instead of 25 RG from the black hole. And this is what we see. These are different scales. This is the innermost region. This is slightly larger region, even larger region. And this is very big distance away from the system. And you see there is a lot of mass here, but still this does not form, but this is more like a very large cloud that is forming. You see this, there is a very strong shock here in this case, but the shock is a different role than what otherwise you would expected. What the shock is doing mostly, it is diverting the flow. So initially, we have this upsidal precession is giving a strong shock, but then this shock here near the black hole divert the flow to a larger distance, and this flow which is diverted to larger distance sort of counteract against the upsidal precession, and overall we have something which again resembles the picture that I've shown before, with a very large cloud which is forming. You can see here, this is the large scale picture, the size of the cloud, a few hundred to almost 1,000 RG. And you can see the stream keep going in, and it's being pushed away from the vicinity of the black hole. And this goes on for another 10 seconds until the end of the simulation, which was about, if I'm not mistaken, about more than 500,000 gravitational timescales. So it's almost a month. 600,000 gravitational timescale. Gravitational timescale is about 1 second here. So it's 600,000 seconds. So it's about 2 weeks. So this is this effect. However, we can still ask, what about GR? And we can go, before that, we can, what about the inverse energy crisis? And what happened to this energy? And there are various solutions that have been suggested. One was gone with the wind, but this work with Tatsuya Matsumoto, which I don't have time to get into it, have shown that this observationally, this is ruled out. There's the idea that the radiation is reprocessed and it's converted from X-ray to optical UV. This is possible, but this does not solve where the energy is going. If it's reprocessed, it should come out. So these two things are sort of ruled out. One possibility is simply that this could direct most of the energy directly to the black hole it falls in, or there is a ballistic infall. It's the same story. And a second possibility is the last possibility is the last disk forms on a longer time scale and it emits in optical and X-rays. So this is the last possibility, and this is actually, given the simulations that you have seen before, is the favored one. This is a calculation of, the disk is very eccentric, so we have to check that it will really accrete. And for accretion, you need MRI, and we do see MRI here. And we have an observational confirmation of this picture. And the observational confirmation is that some TDEs, many TDEs that have been observed for about 10 years time scale, continue to emit on this long time scale. This is the prompt emission, 10 to the 50.5 ergs. But then we see accumulating on the 10-year time scale, 10 to the 51 ergs in UV, another 10 to the 51 ergs in X-ray. And this means that the system will simply go on for about 100 years or more, emitting more and more energy. And this is the solution for the story. Big cloud is formed and not. So most of the debris does not come near the black hole for many years. So this means that if we have a TDE, we should be able to, should expect to see it active in X-rays for about 1,000 years or something like this. We won't know that it was a TDE because it will be a steady source. So it will be simply a steady source in the galactic center, and it may be difficult to distinguish between it and a regular AGN. So before concluding, I want to show you different types of TDE. How close the black hole, how close the star passes to the black hole is the critical factor. If it passes outside the tidal radius, we can still have something. We can have a partial TDE, in which case only part of the envelope is disrupted. And these stars, such a star may come back for a second round later on. And there have been at least 2 or 3 events in which we see double peak TDEs separated by few years. And this may be this partial TDEs. These are the range between 25 to 10 RG when we have regular TDEs. Then there is a region in which we may have strong deflection, and we probably don't have surprises here, we don't know. But then comes the region of extreme TDE. And this is such a nice relativistic story that I must tell you that. Extreme TDE happens when the pericenter of the approaching star is very close to the black hole, 4 to 6 RG. On this trajectory, if the star was not disrupted, it would have made few turns around the black hole before going out. It would come, make few turns, and then go out. But it is disrupted in this process. And this is what is happening. And this is what's happening shown here on the top row. And this is to contrast with regular TDE. This is snapshot from a regular TDE, the disruption moment, the spreading moment, the stretching and spreading, and then the formation of the large cloud. Here, the disruption look completely different. It looks like a spiral. Half of the star goes immediately into the black hole. The unbound half make this spiral, and then the spiral make eventually a ring, And eventually this material from the ring fall back onto the black hole. And this can be summarized here in this movie, which you see here. This is the temperature, this is the density. And you see here the disrupted star. You see here on the background what would have been the initial orbit. And now you see the evolution. And you think that this is frozen, but it is not, because the scale is growing here all the time. So the star is actually moving outwards, and some material begin to fall back onto the center. This is the matter which is falling back into the center. And this was again calculation that was done by Tao Yu together with Julian Colling and myself. And this and here there is something which is a strong X-ray source, which will rise on a very short time scale and will be emitting. And we are trying to repeat this calculation now to get more details on the exact light curve that we can expect from this system. So this brings me to the end of my talk. The end of my talk, I can summarize it as a paradigm change. And the paradigm change is the TDE do not form a small accretion disk. You will say, why do I care? I mean, this is just a detail, and people who are interested in TDE can argue among themselves what is going on. Why should I care about these details? You should care because tidal disruption events are the best way, or possibly the only way, to explore dormant supermassive black hole. There is no other way that you can explore them. And this is the majority of the supermassive black hole, because only AGN, which we can see, are only a very small fraction, less than 10%. Most of the black holes are dormant, and we can explore them only through TDEs. To explore them, we need a model that can relate the mass of the black hole and the mass of the star to what we see. If we use these ideas of a small accretion disk to interpret the observation, we get wrong results for the mass of the black hole and for the mass of the star. And these results are very important for us as a community, because especially the question of what is the mass distribution of dormant black holes in galactic centers, because this has implication to so many things, including LISA observations and so on. So this is why this paradigm change is critical, not just for me, that I'm interested in how stars are torn by black holes, but for a very large part of the community. On the technical level, we argue that the prompt optical TDE pulse comes from the outer shocks. Prompt luminosity actually peaks around the intermediate mass black hole, more or less the mass of our black hole at the galactic center. And by the way, there is another story about what is the impact of this tidal disruption event on galactic centers. I, of course, don't have time to get to this here. This is an interesting topic for another lecture on its own. And so the event rate should peak around these masses, because this is where they are most luminous. Then, after a few T0, which is few months, the cloud settled down to a very large accretion disk, not a small accretion disk, large accretion disk, which may survive for a few hundred to a few thousand years as a steady AGN source. And a few TDEs in which they passed, the initial star would have passed very close to the black hole. They are rare, but not that rare. Will look very different, and we should very, very carefully look for them, because they could tell us a lot about general relativity, almost on the edge of these supermassive black holes. I just see that I ran out of time. I finished exactly on time, so I want to thank you for your attention.
Thank you very much, Three. And we will have some discussion about this topic in the line of Red Dots by Shurui Zhang tomorrow or the day after. And we'll let you know because that could be interesting for you to see the action of merging red dots. But in the meantime, thank you for the beautiful talk, and it's a pleasure to see you splendidly well and with a lot of energy. Thanks.
Thank you. I'm sorry I couldn't come. I was actually planning to come, but you know, my doctor saw differently.
Thank you very much. We are going fast to the next speaker, the last one for this morning. Yes, there is another one.
Because it's already 1:15.
Yes.
We cannot. We will be first in the afternoon. Is that okay? Yeah, sure. The first is Giorgio Met, who is talking online. Excuse me? Giorgio Met. He is talking online. So yes, it's okay. We will for the speaker and for us.
See you in next session in afternoon at 15.
Okay, we start the first speaker this afternoon section, talking about X-ray parameters and a black hole X-ray binary, result and model. Please.
Do you hear it now? Okay, perfect. So my name is Vadim. I work in Finland, and it's a pleasure for me to give the invited talk on the X-ray polarimetry of the black holes. And I'll try to make my talk really general, so because the audience is pretty broad. So I will give a short introduction to the field, and then after me, Giorgio Matt, who is a very professional in the field, he will talk more about XP results on some other sources. I will be concentrating on the black hole X-ray binaries mostly. So here is the outline of my talk. First, I will introduce the concept of X-ray binaries. Then I will be talking about polarization. Then I will describe the sources of polarization in X-ray binaries. And I will go to the main observational results. So let's start with the X-ray binary. So to be called an X-ray binary, the star should be a binary star, and it should be bright in X-rays. So to be bright in X-rays, there should be a very efficient source of energy, and the most efficient source of energy in the universe is accretion. It's in fact 10 times more efficient than nuclear reactions. So we know that in binary stars, if they bright in X-rays, there should be going the accretion process. And in the accretion process, the matter from the optical companion star goes towards the black hole or some other compact object. It gets accelerated and gets really hot, up to millions of kelvins, and it radiates X-rays. X-ray binaries are classified usually by a type of donor star. It can be a low mass star, and in that case, the accretion disk is formed around the black hole, and the accretion goes through the Lagrange point, and we have the flow of matter through this point. In high mass X-ray binaries, we have like wind accretion, and the typical star is has a mass of tens of solar masses. And also, X-ray binaries are classified by the type of the accretor. So it can be either the neutron star or the black hole. So in my talk, I will be talking about black hole X-ray binaries. And the main difference between the black hole X-ray binary and neutron star X-ray binary is that neutron star has the surface, and the matter can hit this surface. And it creates a lot of new physics, which is very complicated. So in that sense, black holes are very simple objects in comparison to the neutron stars. So why we are interested in X-ray binaries? Because they have a lot of different sources of radiation. So we have the accretion disk around the compact object. We have the donor star. We have the flow of matter. We have the X-ray heating of the surface of the star. We have the jet. And it shows really complicated structures on the spectrum of the sources. And those spectra, they evolve drastically during different state transitions in the sources. So here I show you the very famous spectra of one source, Cygnus X1. It's the high mass X-ray binary, and it can be soft when so this is the X-ray energy, and this is the flux. So it can be in the soft state where the spectrum is dominated by the black body emission of the accretion disk, but also it can transition to the so-called hard state when the spectrum is the power law, and it cannot be described with the thermal emission. So, and it's pretty hard to distinguish different sources of radiation if we look at the spectrum only. So we need to have some source of additional information, And from the title of my talk, you can guess that it's polarization. So what is polarization? Polarization is the property of the electromagnetic waves that describes the preferred direction of the electric field oscillations. So if the waves are polarized in random directions, the total light is unpolarized. But if we pass it through the linear polarizer, only the light with some certain orientation of the electric field oscillation will survive, and this light is called linearly polarized light. And the real life example of unpolarized light is the light of the star, because the light is produced at different parts of the stellar surface, which don't know about each other. So the orientation of the polarization is random, and the total emission is unpolarized. But the moment you reflect this light from some surface, for example, the surface of the glass or the water or the road, the reflected light gets linearly polarized, because it's really easy to get electrons moving sideways in the matter than up and down in the matter. So because of that, the reflected light is linearly polarized. And you can see it, for example, here. This is two images of the window in the daylight without and with polarized glasses. And so you can try it yourself. You can try to rotate your head while wearing the polarized glasses, and at some point you will see that the glass disappears, because you actually you just cut off all the polarized emission which is reflected. So the polarization is described by the so-called Stokes parameters. We calculate them from the amplitudes of electric field oscillations, and it's probably very known. But in astronomy, we mostly use linear polarization, because there are a lot of sources of linear polarization, but not so many of circular polarization. And those, the linear polarization is described with two numbers, Stokes parameters Q and U, or alternatively with the polarization degree and polarization angle. So the polarization degree, the polarization angle shows the direction of the predominant oscillations of the electric field on the sky, and we define it relative to the direction to the north. So this is the angle of the polarization of some object on the sky, and the fraction of the polarized emission is described by the polarization degree. Polarized radiation is produced in several physical processes that are taking place in black hole X-ray binaries. For example, in the synchrotron radiation in the presence of magnetic field, or in the scatterings when we have the, for example, Thomson scattering or Compton scattering. And the polarization degree and polarization angle, they tell us about the geometrical properties of the emitting or scattering medium. So knowing the polarization, we can learn something about the geometry. And why the polarization is important in the case of black hole X-ray binaries, there is a good example of the paper of Lee, Narayan, and McClintock. It's a pretty famous one. So this graph shows the spectrum of X-ray binary, like modeled spectrum for different inclinations from 80 to 40 degrees, but at the same time for different spins of the black hole. And you see that they are indistinguishable from each other. All the spectra are overlapping. So you cannot tell what changes the spectrum, the inclination or the spin of the black hole. However, if you plot the spectra of the polarization, so here I plot the polarization degree, and this is the photon energy. And here you see that for different spins and for different inclinations, you can actually distinguish those cases. And that's why polarization is very important if you want to learn something about the spin of the black hole. So what contributes to the polarization in black hole X-ray binaries? First of all, the disk. Usually we think of the disk as a plane parallel electron scattering dominated atmosphere, and there is a very famous formula from Sunayev Tatarchuk that tells you that the polarization coming from the accretion disk in case of electron dominated scattering is has the upper limit of 11.7% if we look at the disk from edge on. So this is the maximum limit on the polarization degree, and it gets to the 0 if we have inclination of 0. So basically, by knowing the polarization degree coming from the accretion disk, we can learn something about the inclination of this disk on the sky. Also, we have some medium around the black hole accretion disk. We call it corona. We don't know what is the geometry of this corona. At least now we know better, but we still have the discussion of what it is. We kind of agree that it's hot, optically thin plasma surrounding the black hole accretion disk. And we agree that in the hard state, we have X-rays coming from the disk. They get scattered in the corona, and we have Compton spectrum in X-rays. Also, jet or outflow can contribute to the polarization because, in principle, the synchrotron emission is highly polarized. However, we don't see it much in black hole X-ray binaries in X-rays, and even in radio, which was surprising to me, the radio polarization is quite small, which is surprising. I think it was detected only for a couple of black hole X-ray binaries. So the synchrotron emission is not very important in terms of like even radio polarization, but also in X-ray polarization. Also, some effects can modify the polarization. The first one is the gravitational lensing. Here I show you the simulation of the accretion disks at different inclinations and for different spins. And the arrows, they show the direction and the polarization degree coming from the accretion disk. So you see how it grows with the inclination, but also you see slight rotations of the polarization angle resulted from the gravitational lensing. So in principle, if we can detect the polarization and if we see the rotations of the polarization angle coming from different parts of the accretion disk, we can learn something about the GR effects. Also, beaming is important because if the disk is rotating, we see incoming part of the disk much brighter, and so it affects the polarization also. There is also a returning radiation, which means that the photons from the accretion disk, that they can go around the black hole and then they can get reflected and go to the observer. And this can modify the polarization drastically because you basically change the plane of the scattering and you change the polarization angle of the radiation. And finally, we can have Faraday rotation. So if we have the radiation from the accretion disk and some magnetized plasma above the disk, the radiation going through the magnetized plasma, it gets depolarized and the polarization angle gets rotated. And this is the law how it is rotated. So for some magnetic field strengths of about 10 to 6 or 10 to 7, it becomes really important, even in the X-rays. So this graph shows you the prediction of the rotation of the polarization angle coming from the disk if it goes through the magnetized plasma. And this is in principle also detectable even in the X-rays. So now we are motivated to study X-ray polarization, but is it really possible? Since 2021, it is possible because XP Imaging X-ray Polarimetry Explorer, the Italo-American satellite, was launched because you cannot detect X-rays on the Earth because of the atmosphere, so you have to launch your instruments in the space. And this satellite was launched in 2021, and in 5 years now, we have more than 200 papers discussing XP results. And Georgia, after me, will discuss a lot of stuff about AGNs, magnetars, neutron stars, pulsars, and I will concentrate mostly on the black holes. And in the future, we will have even better instrument, which is EXTP. It will be launched in 2030, and it will be 3 times better than the XP instrument that we have now. So Since the launch, 15 black hole X-ray binaries have been observed, and non-zero X-ray polarization has been detected in 12 of them, which is great. And here I show you some sources that were observed in these 5 years. And now I will discuss some of the best results. It's of course very biased review, but I've chosen 3 targets to talk about. And the first one is the Cygnus X1. This is the first observed black hole X-ray binary for which we were able to measure the X-ray polarization. On the left slide, I show you the image of the Cygnus X1. So Cygnus X1 is the high mass X-ray binary with a black hole of the mass of about 20 solar masses and 40 solar masses stellar companion. And here I show you the radio image of the jet of this X-ray binary. And on the right, I show you the illustration, the possible geometry of the source. And we see the jet, and we expect the accretion disk to be perpendicular to the jet. So after the launch of XP, before it, there were basically 2 different options for expected polarization of the source. So some models predicted that polarization should be parallel to the accretion disk. So if it comes from some structure which is vertically extended, it should have the polarization perpendicular to the jet. And the other set of models said that X-ray polarization should be parallel to the jet, and it means that in that case the radiation is coming from some structure which is radially extended in the plane of the disk. So basically there were 2 opposite models predicting the X-ray polarization. And in 2021, we measured the, actually 2022, we were able to measure the X-ray polarization of the source. And orange lines here, they show you the polarization angle in X-rays. And it perfectly coincides with the direction of the radio jet. And what it did to the field, it basically ruled out all the models that were predicting the opposite case, the parallel polarization to the accretion disk. And here I show you the very complicated plot. I hope we will survive it, but what it shows the polarization degree. It's the radial direction here, and the polarization angle is shown by these marks. And this black line is the assumed spin axis. So it's basically the angle of the jet on the sky. And the blue point here is the actual measurement of XP. You see that the angle is overlapping really perfectly with the jet of the source. And here I show some predictions of other models. So for example, this is the prediction of the spherical lamppost model, which is the corona above the accretion disk, which is vertically extended. And you see that it predicts very different polarization angle from what we see. So basically all these models, they were ruled out. And what we have now is the models of the radially extended corona. So this is the black hole, this is the accretion disk, and we have some scatterings of the accretion disk radiation in this hot gas, which is extended horizontally. However, we know that the source is inclined by 27 degrees, but here on the zoomed in image, you see that the models predict this polarization degree for much higher inclination of about 45 degrees. So even though the polarization angle is very consistent with those models, something is off because the polarization that we see, which is about 4 or 5%, is much higher than we expected from those models. So some suggestions, so the very basic explanation for this can be that the inner parts of the accretion disk are a bit misaligned with the jet. So if the inner parts where the X-rays are produced is inclined a bit more by 10 degrees, we can produce this polarization. And to test it, I organized the XP campaign on this Cygnus X1 source. And for the first time, we were able to see that actually the polarization angle, which I show here, it changes with the orbital period of the source. And this is the polarization degree and polarization angle of the source versus the orbital phase. So now we propose very simple explanation that the inner parts of the accretion disk is inclined a bit, and it's basically precessing around the orbital axis. And this simple model can reproduce the data pretty well. However, there are other explanations for this. For example, we can have scatterings in some shocks around the source. So, but basically, to explain the variations we see in the polarization angle and polarization degree, we should involve some asymmetry of the scattering medium or the radiative medium. So this was the very big thing in the field. Some other models that can explain the high polarization degree from those sources in the hard state involve the outflowing corona. For example, the corona, the plasma that scatters the light, it can go really fast with the velocity of about 0.5 speed of light. And because of that, the emission is beamed towards you. So the polarized fraction is higher in that case. Also, we can have the scattering in the wind. It also can explain well the high polarization degree in the sources. Or we can have scattering at the jet outflow interface. So there are many explanations now in the field for high polarization that we see from those sources. And here I will show you a couple of more pretty dense plots, but the idea is simple. As I said, the polarization in X-rays can tell you something about the spin of the black hole. So in the soft state, where you see the emission coming only from the accretion disk, depending on the inner radius of the accretion disk, you can basically determine the spin of the black hole. So in this paper, the spectrum of the source was modeled simultaneously with the polarization degree and polarization angle. And as a result of this modeling, was shown that the spin of the black hole should be really high. And the dominant role of the polarization production is in the returning radiation that I explained to you later. However, we should take these results with a pinch of salt, grain of salt, because there are some other papers which try to involve different modeling. And I'm not going to go to the details because it's too technical, but what other papers claim is that it is possible to explain both the spectra of the sources and the polarization degree if you have the spin of the black hole equal to 0. So there is now a very huge discussion. So it's really recent results. And in our group, we also work on that. So one of our students, Anastasia Bocharova, she is working on the modeling of Cygnus X1 soft state data. And also what she gets the spin of the black hole equal to 0. So we don't need to involve highly spinning black holes to explain the soft state data. But the takeaway message from here is that if we increase the quality of the data, because here you see 5 points with the high error bars, if we increase the quality of the data, in principle in the future, the X-ray polarization can be really helpful if we want to study the spins of the black holes. It's a very unique source of information. So now I'm slowly moving to a couple of other sources. I still have a couple of minutes. So another source is Swift J1727, this long phone number. And this source is unique. It's another it's a low mass X-ray binary, which shows the very typical behavior for these sources. Here I show you the hardness of the spectrum, hardness ratio, which is basically the fraction, the ratio of the high energy X-ray emission to the low energy X-ray emission. So this tells you about the hardness of the spectrum. And this is the photon flux. And usually low mass X-ray binaries, they go through the outbursts, starting from the hard state with a very low photon flux, and then they go all the way up, and then go to the left, and go back to the hard state. This is so-called Q diagram for the low mass X-ray binaries, and this source was exceptional because we were able to cut it. Perfect. We were able to catch it in the whole transition from the very bright hard state, and then it changed the luminosity by the factor of 100, and we were able to measure the polarization in all these states. And here I show you the results, and what you see is that polarization degree is almost identical in this region. So I can zoom in a little bit. So even though the luminosity is different by a factor of 100, you have almost the same polarization degree and polarization angle. And it tells you that the geometry of the emitting region in this hard state stays the same while the luminosity changes by a factor of 100. And the last source, actually the last scientific slide I have, is about the Cygnus X3. And this is the unique source because it shows very, very high polarization degree of up to 30 degrees. And it's really, really hard to create high polarization. And the only viable explanation for this was that you hide all the X-ray source by the thick, optically thick walls. And all the emission you see in X-rays is coming from the walls of this cylinder. So basically all you have is the reflection, and you don't see any direct emission from the source. And this is really unique, and it resulted in the, I guess, Nature Astronomy paper. And this is the very good suggestion that the, yeah, I have a typo here, of course. Cygnus X3 is the galactic ULX. So you see only the emission coming from the walls. It means that you don't see the direct emission. So this source should be really uniquely bright. So this is my summary. What XP results on black hole X-ray binaries show us, the main takeaways. So the main one, and I think the whole field agrees on that the polarization tells you about the geometry of the corona, which produces the hard state spectrum of the sources. We all agree that it should be radially extended, so it should be looking kind of like this. It should be radially extended in the plane of the disk and not vertically, as the Lamppost model suggests. Also, we see that X-ray polarization is very stable during the changes of the luminosity, which means a lot, which means that the geometry stays the same during the state transitions. It's also a big result. What we also see, we see that for different sources, we have a pretty consistent behavior of the polarization degree with the hardness. So as the source goes to the hard state, its polarization changes, it grows. So it means that in the hard state, the emission is not thermal, and it's coming from the scatterings in the corona, which also adds more arguments in our models of this emission. And also it provides us some arguments that some sources in our galaxy may be actually ULXs, which is really nice. So this is my final slide, and thank you very much. It's a pleasure.
Well, first of all, I congratulate you and XP for this fantastic work. And as you remember, I was the first to propose the black hole in Cygnus X1 long ago, and give reason for that object being a black hole. Therefore, this was the reason I got the Cressy Morrison Award from the okay. I missed maybe some part of your talk at the beginning, but how you correlate this jetted emission with the hard state and the soft state?
Sorry, what is your question?
How you correlate this jetted emission during the soft state and the hard state of Cygnus X1?
I don't think we correlate the
or what you anti-correlate or whatever.
I think we treat them differently. So we explain the soft state emission as coming from mostly the thermal disk, the accretion disk of the black hole. And in the hard state, we say that we have mostly reflection and scattering in the hot corona. So it's challenging how to connect soft state and hard state now, because we need to understand what is the reason for the transition from the soft state to the hard state. I don't think we have a good model for this. Yes, but I think that's what people are working on right now. So how to connect the soft state.
Look forward to further results.
Any more questions?
Thank you for interesting presentation. It was a picture where light is reflected from a disk. And for this, light must be inclined. And due to what is this inclination? Due to gravity or mainly, or due to deflection in plasma?
So if I understand correctly your question, so here
some other picture where light were inclined and reflected through disk. Yes, this one. This inclination is gravity or plasma?
No, this one is the gravity. So
gravity.
Yeah. So this is the light bending of the light in the gravitational field of the black hole. So the light gets bent and then it's reflected from the other part of the disk. This is the reason why you see the back part of the disk of the accretions.
Yeah. Thank you. Yeah. So can you please explain this? You have a resolved image of the IXP?
No. Yeah, I can explain. So there is a resolved image of Cygnus X1 in radio. So all these contours, they show you. Okay, I will go back. So this is the purely radio image of the Cygnus X1. It shows you the jet. And if we overplot the angle, the polarization angle, which we measure in X-rays, it gives you this line. So this is not the image. It's just the measurement that we show in this way. So this is the polarization angle. And
does it coincide with polarization in radio?
Yes, actually, we were able to measure the polarization in radio for the first time, which was surprising to me. So for the first time, I unfortunately don't have a picture, but it's really beautiful. You can find it in my paper. So what we were able to do, we were able to measure the polarization in optical, radio, and X-rays, and they perfectly coincide. So this is really amazing that structures which are not really connected, the jet and the disk, they produce the polarization with the same angle. So
okay, thanks.
So, last question.
Okay, so I have a follow-up question on that point. So so you mentioned that you had measured in the radio.
Yes.
I'm wondering, have people observed this in the millimeter? And if so, how accurate you can predict the polarization angle?
In radio?
In the millimeter, like 2 millimeter wavelength, like CMB kind of band.
Actually, I'm not an expert in radio. So with radio observations, Andrew Hughes was helping me. He's from Oxford, and he got the time on VLA. So we observed the Cygnus X1 on VLA. Okay. So I don't know the details of radio measurements, but he convinced me that the result that he get is reliable, and it was exceptional because polarization degree was really high. It was, I think, up to 5%, which was not detected before in radio. Yes, but I cannot tell you more, unfortunately, about the radio because I have no experience with working with the data. But you can go and check the paper. It should be written there.
Okay, we thank to speaker. And we move to next talk online.
Tanto cazzo. Mi fa mostrare tutto. Ah, no, l'avete spostato. Ok, l'avete spostato. Ah, scusa. Full screen, eh?
Okay. Are you online? Please go ahead.
Okay, thank you. I hope you can hear me
Can you
and
put
see
full
my
screen?
presentation. If everything is okay, I can start.
Giorgio, ti sentiamo bene. Vai avanti.
So first of all, let me apologize for giving this talk by remote. Unfortunately, a number of academic duties prevented me to join you in Pescara. I'm particularly glad to give a talk on X-ray polarimetry at the Zeldovich conference because I remember my mentor Enrico Costa telling me that in the early 80s, when he and Cesare Perone and Livio Scarsi presented the idea of Italian X-ray satellite, the one which became later on Beposax, to Jakub Zeldovich, Zeldovich asked them whether a polarimeter would be on board. He was quite disappointed when he learned that no polarimeters were expected to be on board. So I think it's particularly fit to give a talk on X-ray polarimetry at the Zeldovich workshop. Okay, I will start with a general introduction on polarimetry, in particular on the Imaging X-ray Polarimetry Explorer, which is so far the satellite dedicated to X-ray polarimetry. Then I will give an inevitably biased selection of XP results. XP now is working for 4.5 years, so the number of results is very large, and of course any selection should be incomplete and biased. And finally, I will spend the last 5 minutes giving an idea of what we can have beyond XP in terms of X-ray polarimetry. Okay, let me start with a general introduction on the imaging X-ray polarimeter. Well, first of all, just to remind you that polarization is one of the characteristics of the observed radiation. So without polarimetric information, any observation is in a sense incomplete. In particular, polarization properties give us information on geometry of the system. Geometry in a very broad sense, in the sense geometry of the emitting matter, of course, when the source is unresolved, but also geometry of magnetic and gravitational fields, of space-time, and so on and so forth. And as a rule of thumb, the polarization degree depends on the level and type of symmetry of the system, while the polarization angle indicates its orientation. No polarimetric observation were available in the X-ray band before XP, apart from one dating back to the 70s on the Crab Nebula, the observation of 90% polarization on the Crab Nebula, which demonstrated beyond any doubt a synchrotron emission was at work in the nebula. But that was the only positive detection we have before XP. The reason why we didn't have any polarimeter after the one on OSO 8 was the fact that there were no good enough detectors matching, at least in a reasonable way, detector for other techniques. But then now we have such a detector, which is the photoelectric detector. So in the end, the Imaging X-ray Polarimetric Explorer was selected by NASA in 2017 in the framework of the SMEX program and launched in December 2021. Okay. Is actually a NASA ASI mission in the sense that Italian is providing the detector, so in a sense the core of the mission. Was launched on December 9, 2021. initially was a 2-year baseline mission as usual. Then everything worked well, so it's now has been extended at least up to 2028 with a general observer program. The current PI is Phil Carré at Marshall Space Flight Center. The former PI was Martin Vaskop. Martin was the PI from the very beginning. He led the mission from the start until a few months after the launch, when everything was clear. It was clear that everything was working well nominally, so he could retire peacefully in a sense. Very sadly, Martin passed away a couple of months ago. I think that to summarize his achievements, better than many words is just to remember his 2 Rossi Prizes he won. In 2004 as a project scientist of Chandra, and in 2024 as the PI of ICRANet. So, in a nutshell, this is the characteristic of ISPE. Is made of 3 identical pair of grating optics and detectors, polarimeters, with about 4-meter focal length. Energy range is relatively narrow, between 2 and 8 kV, let's say the very classical X-ray band. The spatial resolution is 30 arc-second, not so bad, and usually good enough for the majority of our goals. The field of view is 13 arc-minus. The energy resolution is not fantastic because it's typical of a proportional counter. In the end, the detector is basically a proportional counter, so it's about 2 times worse than the CCD-like detectors. The detector principle is based on the photoelectric effect, on the fact that the direction of the photoelectron depends on the electric vector of the absorbed photon. So in a proportional counter, each absorbed and ejected electrons create a track, and from this track you can derive the initial direction, which gives you the direction of the polarization vector of the absorbed photon. So when you collect many photons and plot this many tracks, and plot the direction of this track along the phase, you end up with a modulation like this one, and the amplitude of the modulation gives you the polarization degree of the source, while the position of the peak gives you the polarization angle. The ICRANet baseline mission was funded for 2 years and finished on January 2024, and for these 2 years, the observation program was defined by the ICRANet team. Then NASA extended the mission up to 2028, at least, if everything works well, we hope to be extended even more. And the general observation program is now in place. The deadline for the next call for proposal is mid-September. And we have joint programs with a number of other X-ray facilities, NuSTAR, SWIFT, CRISM, and from this year also XMM Newton, and also with radio facilities. This is very important because for many sources, it's very important to have coordinated or even simultaneous observation with spectroscopic facilities, maybe observing on a broader energy range. So let me give you some, as I say, biased selection of ICRANet result. I will start with is an imaging X-ray polarimeter. So let me start with some results from imaging sources. Before going to details, let just me show the number of the sources we observe in the first 2 years in the baseline mission, just to show that what are the kind of classes we preferentially observed. Not surprisingly, there were compact objects in X-ray binaries, AGN, both radio quiet and blazars, magnetars, and pulsar wind nebulae, supernova remnants. And we have a positive detection in the majority of sources. We started from 1 source observed before ICRANet, the Crab Nebula. Now we have dozens and dozens of sources for which we have a positive detection. Pulsar wind nebulae, well, one of the first observations we want to do was to re-observe the Crab Nebula, just to check whether we could re-obtain the old measurements when integrating over the entire nebula. The also 8 observation was not imaging, so was integrated over the entire nebula. We obtained a result which was fully consistent with the previous observation. Beyond that, we observe much more details because, as you can see here, this is the Chandra image of the Crab Nebula. The nebula is very complex as a sort of jet plus torus pattern, and of course also the polarization is much more complex. In certain specific areas, it's very, very high. And also for other pulsar wind nebula, we observed in some small regions very, very high polarization, 45% or even more, very close in some cases to the synchrotron limit, which means that in those regions, which are small in a sense, but relatively large, of course, because our resolution is not the Chandra one, it's 30 arc seconds. This means that in relatively large regions, we have a very, very ordered magnetic field with very low level of turbulence. Even higher polarization in the cosmic end, the very famous pulsar wind nebula, in which at the end of the jet, we have a polarization which is a little bit larger than 70%. So very, very close to the synchrotron limit. Another imaging observation we performed was on the galactic center. Molecular clouds in the galactic center are bright X-ray sources, and their spectra clearly indicate reflection from external sources. There are no reason why a molecular cloud should be bright in X-rays apart from reflecting radiation from outside. So, are they reflecting X-rays from our own black hole, Sagittarius A star? This has always been the preferred solution for this conundrum. And but if so, Sagittarius A star would have been a luminosity 1,000,000 times larger a few hundred years ago than now. Now Sagittarius A star in X-rays is basically quiescent, very low level emission. And how to check it? Well, X-ray polarimetry is a very clear method to check this hypothesis because X-rays, reflected X-rays should be polarized because quantum scattering polarized radiation, and in particular, the polarization angle would be has to be perpendicular to the radiation, to the direction from the illuminating source and the nebula. So from the polarization angle, one can immediately point out what is the direction from which the radiation, illuminating radiation, is coming. So we made this observation. First of all, we obtain a result a little bit short of the 3 sigma level, but still with a preferred solution very much consistent with the polarization in agreement with what expected if radiation is coming from Sagittarius A star. Then we perform another observation to increase the statistics, and now we have a 4 sigma confidence level that really the illumination is coming from Sagittarius A star. From the polarization degree, you can derive the position of the nebula because of course we have only a projected position from imaging, but with polarization degree you can have a 3D position. So with of course two possible solutions, one in front of Sagittarius A star, one behind Sagittarius A star. And of course these two solutions is also 2 different ages for the burst, for the date for when the burst occurred, about 30 or 200 years ago, and the second solution is much more probable. Remember that during this outburst, Sagittarius A star would have been the brightest source, X-ray source in the skies after the sun. So in 30 years ago, it's very unlikely that such a bright flare, which would have lasted for a year or so, would have been escaped detection. So it's very, very likely that this flare occurred 200 years ago. But anyway, now I would say that the hypothesis that these molecular clouds are reflecting radiation coming from a past outburst Sagittarius A star is, let's say, demonstrated by this observation. Going to compact sources, let's start with magnetars, which are obviously very good candidates for X-ray polarimetry because they have extreme magnetic field. And models expect very, very large polarization. Indeed, we observe a number of sources. We always found very large polarization.
we usually the sources have two components, one thermal, the other one very often due to Compton, and the second one is more polarized. Anyway, what we can derive from this observation is that the surface of this neutron stars is condensed. There is not a gaseous atmosphere, but a condensed at the surface, which was not clear before this kind of observation. And in the third one, we also have an hint of an arc tail with very likely a very, very large polarization, possibly of synchrotron origin. Accreting X-ray pulsars have magnetic field not so extreme, but still very large, of the order of 10 to the 12 Gauss. Also, in these cases, model predicted very large polarization, but probably they were too simple because observations show instead polarization much lower than these probably too simplistic models predicted. In Hercules X1, in which there is a 35 days superorbital period, which has been explained either as a precession of the neutron star of the accretion disk, and the X-ray observation seems to suggest that it is the neutron star which is probably precessing. In a sense, the opposite was found in weakly magnetized neutron stars, in which the magnetic field is much lower, and so the accretion is through an accretion disk rather than a magnetically driven flow. And in this case, instead, we expected very low polarization and found in many of the sources very significant, sometimes pretty large polarization, very often increasing with energy and depending on the observed branch in the color-color diagram. In particular, in zeta sources, zeta are this kind of sources which follows this track in the color-color diagram. We found a polarization degree is higher in the horizontal branch, this one, which is the case in which probably the accretion rate is lower. When the spectrum is decomposed in a thermal disk emission and the Comptonization emission, we found that the polarization is usually dominated by the Comptonization, not surprisingly. But it's very likely that reflection also plays an important role, which may explain the increase, very often found increase with energy of the polarization degree. In some sources, there is a rotation of the polarization angle with energy and or with time, rotation of less than 90 degrees. So this means that there is a breaking of axial symmetry. And finally, during eclipses, in which probably the radiation is dominated by reflection, we have polarization which can be even extreme, up to 30% in a particular source. So it's a very rich and varied phenomenology for this kind of sources. Regarding accreting stellar mass black hole, Vadim just before me presented in detail the case, so I just limit myself to point out that we observe many sources, both persistent and transient. We explore different states, sometimes in the same source, which is very, very important and informative. And we found very often surprising and in some cases very puzzling, I would say not fully understood yet, results. Extragalactic sources, radio quiet AGN. In radio quiet AGN, the emission is expected to be not too different from what we observe in accreting stellar mass black holes in hard state, in which is the hot corona, which provides the bulk of X-ray radiation, at least in the X-ray band. From X-ray spectroscopy, one can constrain the physical parameters of the corona, which typical temperature are of the order of tens of keV and Thomson optical depth of the order of 1 or a few. However, spectroscopy is almost insensitive to the shape and location of the corona, which is important because, of course, not per se, but because the corona, the shape and location of the corona can tell us something about its origin and the way in which it's continuously energized. Polarimetry, on the contrary, of course, is very sensitive to the geometry and so can measure deviation from a spherical symmetry. Unfortunately, in many sources, we observed only an upper limit. Of course, AGN are less bright than galactic sources or the brightest galactic sources, so we need very long observation, and sometimes it's not even enough. So we have a number of upper limits, but at least in one source, we have a marginal detection. And in another source, NGC 4151, not surprising, the brightest radio quiet AGN, we have a clear detection with a polarization degree of 5%, almost 5 sigma detection. And in both cases, 4151 and 4C29A, the polarization angle is aligned with the radio jet, which is pointing out towards a radially extended corona, because a vertically extended corona would give you a polarization perpendicular to the radio jet. So, and I would like to note that this solution is the one we observe also for Cygnus, I mean, a radially extended corona, also for stellar mass accreting black holes in our state, Cygnus S1, and also other sources. It's not clear what is the role of the reflection in this polarization, because, again, I mean, the narrow energy band prevents us to fully decompose spectrally the various components. Blazars are obvious targets for an X-ray polarimeter. You know that blazars are usually composed by two peaks, a synchrotron peak and a second peak, which is probably inverse Compton peak. When we are in the sources in which we are observing the synchrotron peak in the X-ray band, we found always significant polarization, which is not surprising because it's synchrotron emission, so is expected to be polarized. And while in inverse Compton peak, we have much less polarization, and only upper limits are found so far. In both cases, multi-frequency observations are very, 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 very important, because they permit to really discriminate among models. Also for IC peak sources, I will show in a couple of minutes, multi-frequency observation can tell us something about the models. Okay, synchrotron peak sources. The first source we observed was Markarian 401. We have a simultaneous radio and optical polarization. You can see that polarization increased from radio to optical to X-rays. We have a polarization which is aligned with the radio jet, and also studying the variability and all the properties of the polarization in all band, and putting them together, we end up that an energy stratified shock is by far the best model to expect to explain this kind of behavior. Similar observation was found in other sources in the same state, like for instance for Markarian 421, but it's just one observation of this source. A continuous rotation of the polarization angle by more than 360 degrees in 5 days was detected. So there is something more with respect to the simple energy stratified model, at least temporarily, and in this case, probably a localized shock propagating along an helical magnetic structure in the jet is the solution for this particular behavior of the polarization angle. Regarding inverse Compton peak, BLAC itself is one of the sources in which in X-rays we are observing the inverse Compton peak, and we observe only upper limit, but in one of the observation we performed during a multi-frequency campaign, we caught an extraordinary event in the optical. Usually in the optical, the polarization is of the order of 10%, between 10 and 20%, but in this particular state, it reached a very unprecedented peak of almost 50%. While in X-rays, we still have just an upper limit of the order of 6% or so. And this is very constraining, because the ratio between optical to X-rays is telling us what scenario is really at work, between leptonic scenario, Compton scattering, or hadronic one. In particular, all hadronic scenario predicts a much lower optical to X-ray ratio. So a 50% optical polarization would require a 25% or even more X-ray polarization. So the very low, the very tight upper limit on the polarization degree combined with the extreme polarization degree in the optical tell us that the leptonic scenario, and very likely a synchrotron cell Compton probably, is or inverse external Compton, which predicts almost some no polarization X-rays, is at work in this source. So just to summarize the part on the results, XP has really reopened the new observing window. As I said, we went from one observation to several dozens of detected sources. Significant polarization is rather common in X-ray sources, as expected, but even more than expected in a sense. I would say that anytime we have a surprise, usually is a surprise in a sense of more polarization than expected, not less, which was not expected in a sense. And not surprisingly, most of the detection are related to strong magnetic fields, but also scattering polarization is very often detected. And in many cases, results and even upper limits, as I've just shown for BLAC, are discriminating between competing models or challenging popular ones. So let me finish just with a few words about the future. Next and solid, robust future, in a sense, is the Enhanced X-ray Timing and Polarimetry Mission, EXTP, which is Chinese-led mission approved for launch in 2030. And is composed of CCD-like cameras for spectroscopy and timing, and of 3 polarimeters. The polarimeters are very, very similar to the XP1, but with a total effective area about 4 times larger. So the fact that the detector is basically qualitatively the same means that the similar scientific objectives, but reachable, of course, with less exposure times, which mean that then short-term variable objects can be studied in more detail. We can start to have population study for many classes of sources. So far, we have population studies mainly for, let's say, weakly magnetized neutron stars and synchrotron peak blazars. And very importantly, we can have simultaneous high-quality spectroscopy and polarimetry, which is very, very important for many class of sources, in particular for accreting sources. Then, beyond in a more distant and less certain future, we proposed a mission called the Enhanced X-ray Polarimetry Observatory, in response to an ESA call for a medium-sized satellite number 8, with an expected launch of the selected mission in 2041, so in 15 years from now. It is one of the 10 missions which passed the Step 1 selection. Step 2 proposal was submitted in March 2026, and then in November there will be a down selection from 10 to 5 sources, and these 5 sources will start a so-called phase 0 study. Then in November 2027, only 3 sources will survive, and 3 sources will undergo a proper phase A study for a final selection in June 2030. So what is the logic, the rationale behind this proposal? Well, 2 major limitations of XP are a relatively narrow energy range and a very slow repointing capability, which basically prevented us from studying fast transients, GRBs or things like that. We want to overcome this limitation. And so we will have a Swift-like repointing capability, and the payload will include 2 low-energy polarimeters, very similar to the XP1s, but also 3 medium-energy polarimeters, extending the energy range up to 35 keV. We'll have also a spectrometer, a CCD-like one, which can provide simultaneous spectral and timing observation, and we will have also a wide-field monitor, of course, in order to catch transients in the sky. And the effective area is comparable to that of XTP in the same energy range, but of course with a much broader energy range. So scientific objectives, we can divide these objectives in 2 types. One, fast transients. This Swift-like repointing capability will allow us to, for instance, to observe at least part of a GRB We estimate that to observe 5 to 10 GRB per year for which part of the bust can be observed with a minimum detectable polarization down to 1%. Of course, because the repointing capability, depending of course on where is the source, but is of the order of minutes, we can all, in this case, with this technique, we can only observe long burst. But because a number of events have precursors, and we can catch these precursors, we expect a similar number, 5 to 10 per year, of bursts with the precursors for which the whole burst, so even a short one, can be covered. So we hope to be able to observe both short and long bursts. And of course, in addition, several afterglows can also be studied. Regarding the broadband,
5 more minutes.
Yeah. I'm also done. Regarding the broadband energy, we have several features to observe. Cyclotron lines. Here you can see a plot thanks to Sergei Tsigankov, in which you see a simulation of the a cyclotron line observed with our mission, with IXPO. You see the details with which we can follow a cyclotron line, which of course encodes a lot of information about the neutron star and the magnetosphere in the neutron star. We can study reflection in different environments. Reflection usually peaks at 20, 30 keV. And for instance, as I mentioned, the polarization in 4151 is likely a mixture of polarization from the corona and the polarization from reflection. With IXPE, we couldn't separate the two the two components. For instance, this is the contour plot for the reflection component, which is not constraining anything, while with EXPO, thanks to the broad band, we can clearly separate the two components, so understand whether the polarization, in what fraction the polarization is due to reflection, in what fraction is due to comptonization. And of course, in this case, using this information to really study the geometry of the corona without any contamination by the reflection component. And another example are supernova remnants. I didn't have time to talk about supernova remnants, but in supernova remnants, of course, the bulk of the emission in the X-ray band is thermal emission, so not polarized. We have some tail already observed in some young supernova remnants, which are polarized, but with the broad energy range, of course, we can study in much more details all these are tails. Okay, I think my time is running out, so I stop here, and thanks you for your attention.
Questions? So if there are no any questions, we call next speaker, please.
Thanks. Thanks. And it has been continuing up to now. What is the subject? The key quantity is the energy in the center of mass frame. It turns out that under certain conditions, collisions of two particles near the black hole leads to formally unbounded energy in the center of mass frame. And this was found for rotating black holes, but it is valid also for static electrically charged black holes, for collisions outside and inside. And one should not mix two different processes. The energy in the center of mass frame, which is characteristic of the event in this very point, and the energy measured at infinity as a debris as a result of collision. I will speak on what concerns point one. So after this paper by Banyada Silkvest was published, the effect was called BSW, after the name of his, and people recollected that there was a paper with 3 papers with this office where something similar was considered. But there is a subtle point here. This office considered collisions on circular orbit, which is not the subject of my talk, although maybe it is the most promising area where it can be observed astrophysically, but this is a separate subject. And for collisions of particles moving opposite direction. But the point is that if near the horizon particle moves away from the horizon, this is typical of a white hole, not a black one. So it is more artificial case. And this happens for any two such collisions, but BSW showed that such an effect occurs when two particles move towards the horizon. For instance, they fall from infinity. And an additional condition is one of particle is fine-tuned. How to define the energy in center of mass frame for two particles? For one particle, it is well known from the standard textbook, the relationship between mass and square of momentum. For two particles, in general, in curved space-time, there is no well-defined definition, but happily it exists if we define it in the same point where collision occurs. It is quite sufficient. It is total momentum. So in the rest frame, it looks like some standard expression. If we compare it with standard Killing energy, we see a difference. Killing energy arises because of staticity of the metric or its stationary character, and it is connected to corresponding Killing vector. But energy in the center of mass frame is not concerned, and moreover, it is defined in one point only, point of collision. So we concentrate on this quantity. This is taken from this BSW paper. You see two particles fall towards a black hole of extremal Kerr metric, and if one of particle has specially fine-tuned parameters, then its energy becomes as large as one likes. Usually in black hole physics, if something happens due to the existence of the horizon, it is not restricted to this very particular metric and has more general character. And this is the case here as well. So practically for any rotating black holes, this effect does exist. And moreover, with some limitations, it is valid also for different types of horizon, not only extremal, but also non-extremal or triple horizon and so on. What does it mean geometrically? Let's write down the metric in the light-like basis, 2 light vectors and 2 spatial vectors. Then we can expand the velocity of a particle with respect to this basis, and the scalar product of these 2 particles is expressed like this. Meanwhile, the total energy in the center of mass frame, according to the previous formula, is given just by this quantity. So the key role is played by this scalar product. It has the meaning of Lorentz gamma factor of relative motion. And you see here there are 2 coefficients in the denominator. And if one of them is very small, the energy becomes very large. And what does it mean? If such a coefficient is small, it means that particle moves almost along the horizon. It cannot move in this direction because the coefficient is small. So in this limit, the energy tends to infinity. Or if one calculate the proper time, it turns. So you see here, usual particle. Usual, it means that it has arbitrary parameters, energy and angular momentum. And C, critical particle, by definition, it means that there is some special relation between energy and angular momentum. And in doing so, the proper time to reach the horizon is infinite. It means that, strictly speaking, such a collision never occurs, but it can be arranged closer and closer to the horizon. I consider the metric of a generic form, stationary without dependence on angle phi. And then it follows from the geodesic equations that for velocity of a test particle can be written in this form. Here, P is something like momentum. And this combination enters, it's typical, epsilon and energy and angular momentum per unit mass. So energy of collision of such a particle is given by this quite simple formula. And you see this quantity in the denominator which vanishes on the horizon by definition. But the point is that typically numerator also vanishes in this point, and this is the reason why this effect in general does not exist and requires some fine-tuning. And how it can be explained kinematically? Although it is effect inherent to black holes, explanation is very simple and comes from physics in flat space-time. Let's consider collision in flat space-time. Then the gamma factor can be related to the relative velocity. And as we know, this formula can be found in textbooks. If one of particle has some finite velocity less than 1 in dimensionless units, one is the speed of light, and the other particle has velocity close to the speed of light, then the relative velocity can become as large as one likes. And we have the following relations. To make some calculations on physically meaningful quantities, we must attach some tetrad to an observer. Here, the simplest choice is exploited zero angular momentum observer, in which the tetrad looks like this, very simple. And one can derive this formula. This is so expanded form of the energy conservation, energy of momentum. If we approach the horizon, n tends to 0. For usual particle orbital relations, it means that v tends to 1, so it compensates it. But for critical particle, the left-hand side itself vanishes, so v can be equal to some value less than 1. And this is just situation which I described just now for flat space-time. And also, there are some useful formulas for kinematics which expresses 4 velocities in terms of free velocities here. And in the horizon limit, we see that in the long beach of 4 velocity, for usual particle, it remains some quantity non-zero, and in the critical particle, it tends to 0. So roughly speaking, it stops on the horizon. And what 5? Okay, I will skip details. It was shown that it exists for non-extremal horizon as well, and here for non-extremal the critical particle cannot penetrate the potential barrier, but if we admit some deviation from the extremality and tuned to the distance from the horizon, then collision can happen in this small region where the same growth occurs. In generalization, what does it mean? We consider metrics of a general form expanding the Taylor series near the horizon. So we have 3 quantities, usually integers, and also we admit some finite force. And you see the table is composed in which it is shown which combinations of different types of particles leads to this effect, and in which case it does not. Here, more rigorous definition. Generally, you see not 2 but 4 types of particle depending on behavior near the horizon. And see, I skip it. And this is a general approach, gives our table. And we admit the existence of some force, and we define quantities n naught and 1 and 2, which characterize the behavior of the force near the horizon. So we, given these three quantities and these three quantities, we can scrutinize gamma and find what happens. Here we consider case by case different combinations, and you see, so this is quite complicated table, but it allows to find the answer. Given all these 6 numbers, we can tell you whether or not the effect is possible. And there is a subtlety here. This is the principle of kinematic censorship. In any event, the energy cannot be literally infinite. So if in some scenario we obtain infinite energy, it means that something wrong. For instance, for external black holes, it's infinite only for infinite proper time, so the collision never occurs. In more subtle cases, either force becomes infinite or geometry becomes singular. It is proved by us. So, and up to now, I considered equatorial motion. For non-equatorial motion, situation is more complicated. Only in some belt high energy collisions are possible, but it turns out that all this picture does not affect the principle of this classification. It is valid as well. And moreover, this type of classification is built not only for fine-tuned particles, but also for near fine-tuned particles, which in the simplest case of non-extremal black holes ensures, as I showed, effect inside the potential barrier. It means that this key quantity starts not from this term, but also has something non-zero. And again, we repeat classification. Instead of critical, we have near critical, and instead of near subcritical, near also near subcritical. But one new type of particles appears, which was absent in the pure case. It is near overcritical. This is behavior of gamma factor is given. The finiteness of force is restricted by some conditions. You see a lot of different cases and subcases. And similar to black holes, there exists, for instance, the effect of high energy particle collision if one particle enters the wormhole from one mouth and the second one from another mouth. This was observed by Krasnikov. And so the effect is more general. It concerns not only black holes. Let me summarize. We constructed the general scheme which accounts the action of a finite force, different types of horizon, and checked the validity of kinematic censorship. In spite of its obvious formulation, it is not always trivial as it happened in discussion on collisions inside the horizon. So in some sense, if not the full theory, but the piece of theory which deals with particle collisions, volatile electromagnetic field near black holes is built in closed form. Thank you.
Okay, thanks to your talk. These results are very interesting, but I want to ask, did you consider some realistic particle collision and take into account the quantum effect? For example, to electron and positron collision, we know it can produce...
What do you call very realistic?
For example, the electron and the positron collision, and I mean, not just consider
yes,
like this.
The estimates were made for some elementary particles, but I would like to stress that the theory here is pure classical. We didn't consider quantum effects, and quantum effects are weaker. It is somehow it's spread by function, is not localized. So this is classical effect. But yes, you pose the right question about possible astrophysical application. My talk was pure theoretical, and recent preprints argued that the most favorable case when it can give something observational, these circle orbits, but it is quite different subject. I didn't consider it. What you see, generally, if something non-trivial does exist theoretically, sooner or later it will reveal itself, I think.
Okay, so we have a 10 minutes coffee break, and let's back on account for the next half section. Okay, Mr. Kogan, are you ready?
Yes, yes.
Put a full screen.
So I can speak now. Can you hear me?
Yes, I do.
So my talk will be about very dense stars in the uniform density approximation. It's a theoretical consideration. It contains from two unequal parts. First is the critical states of uniform neutron and strange stars, means that the points of loss of stability. And the second part is the discussion about the confinement and possible existence of strange stars. I was a graduate student of Zeldovich who first gave me topic connected with compact stars. So white dwarfs had been the only observed ones, but theoretically neutron stars had been investigated. Starting from Oppenheimer-Volkoff paper, the structure of stars was found solving equations which they derived in the frame of general relativity. Maximum mass they obtained for neutron stars was equal to 0.7 solar masses, and it was too low for being realistic. But later, many authors who took into account the interaction between strong interaction between baryons found that it is could reach 3 solar masses, and their existence was not doubtful. They were discovered very soon. At that time, I also worked on neutron stars, hot neutron stars, maximum mass, and obtained that it could be up to 15 solar masses. The paper was in astrophysics. So all these results have been obtained using a solution of Oppenheimer-Volkoff equation in general relativity. Here we applied the simplified variation method for search of critical states of neutron stars and quark strange stars. Actually, this method was used in 1930 for finding the maximum mass of white dwarfs. This limit now is called the Chandrasekhar limit. But first it was found by English physicist and astronomer Stoner in 1930, who derived the equation of state for relativistic degenerate electrons and used formed models of white dwarfs in uniform density. He used the variational method for obtaining the equilibrium state. In this approximation, uniform approximation of ultra-relativistic degeneracy, he obtained a limiting mass as 1.1 solar masses for mu e equal to 2.5. Mu e is a number of baryons on one electron. The next year, Chandrasekhar, following Stoner idea, improved it considerably. He, instead of uniform model, he considered a more realistic polytropic model with index n equal 3 and obtained white dwarf mass 0.933 because he used the same value of mu as Stoner. The conventional amount of mass of white dwarfs, 1.45 solar masses for mu e equal to 2, as because they are mostly carbon oxygen masses, was obtained by Landau next year, who worked independently on the Stoner and Chandrasekhar. So these three people took into account in this discovery, and the first was a Stoner. Uniform density of neutron star is a more complicated procedure because number density and mass of the neutron of this star are considered as separate integrals. So because mass is contained also the gravitational energy, negative gravitational energy, and number of baryons related to the density of mass without gravity. So these two expression for these values, and for uniform density, it can be integrated exactly, and that leads to the following equilibrium equation. So this universal equilibrium equation is valid for any equation of state, which depends only on ratio of radius to gravitational radius and equation of state. So by choosing corresponding equation of state, we may find critical values for different neutron stars. This is for equation of state, which was used by Oppenheimer-Volkoff. You see the mass of approximate mass is about 10, 15, 20, 10, 20% of actually less than 20% larger than real solar mass. Real was 0.7, and here we have 0.8. Also, we have found the maximum mass for other equation of states. For example, this one is for obtained for result obtained for the equation of state obtained by Bethe in his work of 75, which contains many many different equation of states, and here up to two solar masses, one of them. So the comparison of results for uniform density masses with exact solution for various equation of state from Bethe et al. 75 show that approximate value of the critical mass of star exceed the exact value by at most 50%, 20%, sorry. Critical density in uniform critical densities in uniform density observation, of course, are significantly lower than the value of critical density of numerical models, because in numerical models there are central densities, and here there are average densities, and the average densities are much more closer. About uniform density strange stars, we have used equation of states of MIT Begg model, Quark-Begg model, which is used now and is considered as more or less realistic for strange stars, which have strange properties with very big density at zero pressure. So the surface of the strange stars is a very dense, very big density, but zero pressure. This is MIT Beck reflect these properties. In uniform density approximation, it is considered as algebraic equation. All equations are integrals are taken analytically, and we have the same equation of equilibrium as was shown for neutron stars, and found maximum loss of stability happens at equal ratio of radius to the gravitational radius. So x is one really unique value equal to 0.815. So for different values of b is the value connected with the confinement point where quarks becomes almost free and form quark-gluon plasma. And even if one of these quark is strange quark, then we have a strange stars with this strange equation of state described by MIT Big model. And so for different b, it's b has a measure in rho same no it's just proportional to density. So b in this math over cubic Fermi is transformed into density in 10 to 15. So we see here the b low b correspond to low density, and high b correspond to high density, and mass goes opposite. So for low b we have a maximum big mass, sufficiently big mass, and for lower for higher b we have smaller mass. So this mass is exceed in some cases, in some equation of state, the maximum mass of neutron star. So the neutron star, in principle, can lose its stability and be transformed, compressed, this forming such a strange
You have 3
quark
minutes
stars.
more.
What time I have?
You can have another 3 minutes.
So I have only 2 or 3 minutes, not more.
Okay.
So these are for different b, you have different curves for dependence of m over r, and this is m over density, this is m over r. And finally, a few words about the experimental results. Experimental results for finding b are based on the estimation of density after which the matter becomes a quark-gluon plasma. And all these values are much larger than the values which are usually used for construction of strange quark stars, which are based on theoretical investigations, very approximate with many simplification and so on. And I would incline to believe more in experimental, because theory needs further improvements because it's very approximate. And therefore, coming to conclusion, but it's not a conclusion, but it's instead of conclusion, because we cannot now make a definite statement, but we can make a very realistic suggestion that basing on experimental results, we find the density of the confinement, which corresponds to very small solar mass, small mass of the strange stars, which cannot be formed in the process of usual stellar evolution. But so it seems in that case we would not be possible to expect. But we must remember that such a high density in strange stars, the uniforms is crossed during its expansion at very at large. The redshift maybe thousands, not thousands, but billions. The density is correspond to density of this such a strange star, and similar to formation of primordial black holes, which are also could be formed only at very large density with a perturbation, but giving larger density. So this perturbation, if it is appeared not maybe the same time as black hole and which are small perturbation, so they have a very big barrier to cross in order to become a primordial black hole. And if they don't cross this barrier, they could remain strange stars. So we may expect now such a strange stars as remnant of observation, which we may call it primordial strange stars, in analogy with primordial black holes. And finally, I would like to show the two papers, very recent papers, where these uniform density models are found. And thank you very much for your attention. That's all.
Questions? Questions? So if you know, let's move to next speaker.
If there are questions, then please
No.
louder, because I cannot hear.
No, no questions. So next speaker.
Thank you.
Thank you again. Next speaker, please be ready. B son. Okay, he's a person. This guy is a person. But where he is? Where is this B son?
one too.
Ah, thank you. Okay. No, see?
No, I feel. Okay, we're going.
Mm-hmm. Good evening. No, see? Uh-huh. Good evening, everyone, and it's my thank you for opportunity.
Can you hear?
To present my
Hello?
work. Yeah.
Oh, use this one.
Ah, okay. It's my talk is about gravitational refraction of compact objects. Next presentation. Compact objects with quadrupole momentum. And the main idea of to describe light distinguish the gravitational field as propagation in an effective optical medium. In this language, the gravitational field is represented by an effective refractive index. The central question of this talk is very simple, and can an optical signal distinguish a slowly rotating compact object from a statically deformed one? I will show that at first order and in the weak field regime there is an optical mimicking effect between these two cases. And I am needed to let briefly outline of my talk, and there are 4 steps. First, I will explain the physical motivation. Realistic compact objects are not exactly spherically, are not purely Schwarzschild. And second, I will introduce the material medium formulation where light bending is written in terms of an effective refractive index. And the third is I will compare 2 sectors and the static quadrupolar deformation and the slowly rotating space-time. And finally, I will discuss the main result, namely the first order mimic relations and its implication for parameter interference. So the getting question is, can I, with optical signal, tell us whether the source is rotating or statically deformed one? And why quadrupoles matter? The motivation comes from compact objects optics. The simplest Schwarzschild case, the optical signal is mainly controlled by the mass. But realistic compact objects are more complicated. They can have mass, angular momentum, and a multiple structure, including a quadrupole moment. These additional properties can modify the propagation of light. In the material medium picture, light deflection can be interpreted as a refraction in an inhomogeneous effective medium. The diagnostic problem is that different physical mechanisms, many generate similar first-order optical corrections. In this talk, I compare 2 mechanisms and a static deformation described by the parameter quadrupole moment and the slow rotating described by the spin parameter and the equals and object over mass. The important point is that both mechanisms affect the same optical observable, namely the effective refractive index. There is mistake. There's instead this row and methods. Now introduce the methods. The material medium approach rewrites light propagation in covered spacetime as light propagation in an effective optical medium. For static metric, written in isotropic form, the line element can be written as times and the squared minus b times the spiritual line element. For light, the interval is 0, so you can identify effective velocity of light. That means that the gravitational field behaves like an inhomogeneous optical medium. The practical pipeline is the following. Start from the metric, transform to isotropic coordinates, compute the light velocity, obtain the refractive index, and then compute the deflection angle. The same pipeline is applied to the static and rotating sectors, so the comparison is made at the same optical level. Next, static deformation sector. Let us start with the static quadrupolar sector. The source is described by an approximate static metric with two parameters, the mass parameter and the quadrupole deformation parameter Q. After applying the material medium procedure, we obtain the refractive index shown on the slide. The first factor is the Schwarzschild contribution. Indeed, when quadrupole moment equals 0, the result reduces to the Schwarzschild refractive index. The second term proportional to quadrupole moment is the first order optical imprint of the static quadrupolar deformation. If Q is the positive, the refractive contributions is enhanced, and if Q is the negative, the refractive contributions is reduced. For the present discussion, the control its physical region is the weak field, external region outside the compact object. From the refractive index, we can calculate the weak field bending angle. In the static quadrupole sector, the result has a very simple form. It is the Schwarzschild bending term for a mass of over radius multiplied by 1 plus Q over 2. So the quadrupole parameter gives a linear section and it's important to stress the domain of validity here. This is not a strong field result. It's a first order weak field correction in the static quadrupole sectors. What's happened? Grigory? Presentation stop. What's happened? Stop. Not moved. Yeah. This one? And the slow rotation refraction. This one. Thank you. And now we move to the rotating sector. Here the spacetime is described by the linearized Kerr metric. The rotation is characterized by the specific angular momentum where the equals and the index over m. At first order in optical correction comes from frame dragging, and the corresponding refractive index is shown here. And the correction depends on the Spain parameter, impact parameter B, and the radial coordinate R. A very important clarification is needed. The first order correction is a frame dragging correction. It's not the full Kerr quadruple. And because the Kerr quadruple appears at order a squared, therefore, the comparison between the first order static Q corrections and the first order rotating optical corrections. And this slide contains the main result of the talk. We compare the refractive index in the static quadruple sector with the refractive index in the slow rotation sector. At a fixed radius, the first order frame dragging correction can be reproduced by an effective static quadruple. Within this first order weak field approximation, the same optical correction may have two different interpretations, and it may come from slow rotation, or it may be mimicked by a static quadrupolar deformation. Therefore, one weak optical measurement alone does not uniquely identify the physical origin on the signal. This is optical mimicking effect. Let us now discuss that this means for parameter interference. Within the rotating sector model, two refracted rays can be used to form two equations if the effective refractive indexes measured for two rays, then in principle one can solve for the mass m and the Spain parameter a. However, because of the mimicking relation, the infrared Spain can also be translated into an effective static quadruple. So the inverse problem is not automatically unique. The main lesson is that additional observables are needed to break the degeneracy. Possible diagnostic include image, morphology, timing, polarization, finite distance, lensing effects, and the strong field photon ring observables. In other words, the refractive index is useful, but it should be combined with complementary information. So, by conclusions is a short summary. Let the First, the material medium approach provides an effective optical description of gravity, the refractive index N or R. Second, both static quadrupolar deformation in the slow rotation modify this refractive index and the bending angle in calculated first-order ways. Third, at a fixed reduce, the first-order rotating sector correction can be mimicked by an effective static quadrupole. And this means that a single wave field optical measurement is not sufficient to identify the physical origin of the signal. The diagnostic message is that the generacy breaking requires complementary observables. A natural extension is to test whether this order degeneracy serves changes or breaks in exact metrics and in strong lensing observables. Thank you. Thank you. I need. No? I need question. Uh-huh.
For the medium that has such refractive index,
Yeah.
mimic
Schwarzschild. Yes. Thank you. It's usual time. Then compact objects have corrected by only mass. There is other case, and the light propagation will be presented the gravitational field as optical medium. It is physical concepts, yeah, from optical, yeah. And this we show that it's the different will be different between rotating case, the objects, and slowly rotating by Schwarzschild case, and and the optical light medium. It's will be compare, and from that will be find the physical items.
Is it working?
Is it on?
I don't know.
No, it's not.
No, all these guys left. Okay.
Use this one? Okay. Is that work?
Who is the next one? This one. Who is the last one?
My presentation is on the website.
What is this?
This one probably, can you check? Yes. Oh, okay. Okay, I can start. Yeah, okay. Okay, hello everyone. Thanks for staying for my talk in the evening. So, yeah, my name is Zina, and I would like to thank the organizers for this opportunity to present our recent work on anisotropic hybrid stars. This is work that I've done with my PhD supervisor, Banibrata Mukhopadhyay. We are at the Indian Institute of Science. So to start with, at the previous edition of this conference, at the previous Zeldovich meeting, we had aimed to talk about this question: how heavy can a neutron star get? So this is, a question that seems simple but doesn't have an answer, and this is because neutron stars are really dense objects, and they are so dense that we don't know what exactly matter behaves like in those regions, and because of this we don't know what the maximum mass they can support is. We have previously shown that massive neutron stars which have structural enhancement from magnetic field and pressure anisotropy could explain objects in the so-called mass gap, which are being increasingly observed. So objects which have masses above 2.5 solar mass while satisfying stability and observational constraints. Now, the goal of the current work which I am talking about is we have tried to add more physics to the problem by looking at additionally superconductivity and deconfined quarks. This work was recently on arXiv, so please feel free to look at it for more details. So, yeah. So to start with, the name neutron star is not a very good name, as we have seen in other talks in this session itself. When we say neutron star, it could mean a number of objects. As you can see, neutron star can contain within kaons, pions, hyperons, and so on. What we are interested in the current discussion is, okay, I don't have a pointer, but it's basically that sector, the hybrid sector, where oh, okay, okay. Yeah, thanks. So this is the hybrid sector, basically this octant, where you have normal matter in the outer layers, and at some high density there is a deconfinement phase transition, and there are some quarks present in the very interior of the star. So a more interesting an alternate scenario is where the quark matter occupies the whole star, but we are not studying that. We are studying this part, which is called a hybrid star. What you'll notice is that when quarks show up, so do these interesting acronyms. So there's this 2SC, CFL, etc. So what does that mean? Essentially, this signifies the onset of color superconductivity. So because of the high densities at which quarks are interacting with each other in the core of the neutron star, we could have them form Cooper pairs and under the color magnetic force, and that's where you can get color superconductivity. So I said that we know very little about the nuclear matter equation of state. Well, we know even less about quark matter equation of state and where the deconfinement happens. So even though there is, some belief that color superconductivity will show up in the star, which density exactly it will show up depends on, for example, what is the mass of the strange quark or the superconducting exact value of the superconducting pairing gap. What is expected is that at high densities, we expect that this color flavor locked superconductivity will show up, where all three flavors of quark matter, up, down, and strange, pair with each other. This is the most symmetric color superconducting state you can have, so it is expected that eventually this will show up in the star. But again, where exactly it shows up, it depends on these other parameters. In between, you may have other non-CFL states as well. And just to bring this all back to the thing I mentioned in the beginning, the question is, can color superconductivity be a source of deformation or anisotropy within the star? Because this can have observable effects. So I'll skip this slide for now, I'll come back to it. But if you want to solve for the structure of the star, we basically need to know its equation of state. So I'm not going into the details, but this is how we model the equation of state of our hybrid star. We have the hadronic part described by DD2. It's a famous density dependent equation, relativistic mean field equation of state in the literature. The quark equation of state is a vector interaction enhanced bag model. So I think a few talks ago people were talking about the bag model. This is basically the bag model plus we allow for the quarks to have vector repulsive interactions between each other. You can see that the hadronic and quark phases are joined by a first order phase transition, and additionally we include color superconducting effects through the pairing energy in the thermodynamic potential. We assume that the entire quark core is CFL color superconducting, so it's basically these three parameters, the bag constant, the vector interaction and the color superconducting gap, that determine how much quark matter is at the core, or in other words they determine where the phase transition happens. So this is the formalism that we use. Basically we now have the modified TOV equations. We follow this from our previous papers. Basically the TOV equations are modified by the presence of magnetic field and anisotropy. We have a magnetic field which varies within the star. It's parameterized by the pressure in this case. And in order to fully describe the system, we need to also have some ansatz for the anisotropy. So this is where, as I mentioned, we wanted to take into account the possible role of superconductivity, right? So as I said, it's not clear, first of all, what type of color superconductivity could arise in the star, and additionally what structural effect it could have. There are many proposals in the literature. So what we have done is we have proposed two phenomenological profiles that can kind of capture the extreme or not extreme, the range of behavior that color superconductivity could have within the star. So our first profile, so both our profiles have basically magnetic field plus superconductivity leading to anisotropy in the star. So in our first profile, I'll just come forward. Our first profile is basically multiplicative. The role of superconductivity is to enhance the already existing magnetic stresses in the star. So this is the form that we have. There are some extra terms to ensure the physicality of the profile. B square is how magnetic stresses enter the anisotropy, and this is the enhancement from superconductivity. So this is a well-known behavior that is followed in, for example, type 2 superconductors, where you can have this mixed phase between the two critical fields. You can have this mixed phase where magnetic field is confined to vortices. In that case, the stress energy tensor is modified by the presence of superconductivity. Similarly, there is a proposal of this magnetized CFL phase where you have magnetic field and superconducting gap kind of coupled to each other. So we kind of take inspiration from that and propose this phenomenological profile. We have worked on this in other contexts as well in the terms of only proton superconductivity. You can see this is gravitational strain as a function of frequency. Superconducting star is more deformed when compared to non-superconducting case. But the other sort of possibility to leave open is that what if superconductivity can bring with it its own pressure anisotropy independent of the magnetic field. 3 minutes more, okay. Okay, fine. Independent of magnetic field. In that case, you can see that we have this proposal which follows the behavior of crystalline color superconducting phases, where you have superconductivity on its own right leading to anisotropic stresses. So these are our two proposals. In the first proposal, if magnetic field is 0, the anisotropy vanishes, but in the second proposal, anisotropy itself can be sourced by the color superconducting gap. Okay, so as I mentioned before, because I'm short of time, I'm not going into all the details here, but one of the main things that anisotropy can do is that it can enhance the mass of the star. Usually the presence of any exotic phase brings with it a softening of the equation of state, so the star is not able to support as much matter. The same thing happens when we consider a hybrid star, especially color superconductivity brings pairing energy. It can lower the phase transition, and more quark matter occupies the star, less mass is supported. You can see that, for example, if you compare the various dotted curves, that the maximum mass goes down, but if we consider some sort of anisotropy from either of our proposals, the mass can reach above 2.5 solar masses. So yeah, without going into the details, basically stars of 2.5, 2.6 solar mass is not ruled out if we consider quark matter to be appearing in the star. The softening can be compensated by anisotropy. We have also shown this in another context. But I'll just move forward to the last part of my talk. Basically, we are talking about anisotropic stars, which means the radial and transverse pressures are not equal. That means the star is no longer spherical, so it is essentially deformed. So we are still within a 1D treatment, so the rest of the deformation and gravitational wave thing will be kind of qualitative rather than quantitative, but we are just trying to establish some trends. So first of all, let's try to see if we can estimate what could be the ellipticity from the various anisotropic stresses that I've mentioned. So first of all, you can see that with the variation of superconducting gap in the star, how we have a magnetic ellipticity, profile 1 and its ellipticity, and profile 2 ellipticity. So magnetic ellipticity is just caused by the deformation of magnetic field just from the magnetic stresses in the star. In profile 1, we allow the superconductivity to enhance that magnetic stress. So you can see that there's a slight increase in the ellipticity, whereas in profile 2, we allow the superconductivity itself to be a source of anisotropy, and there is quite high ellipticities. But why is ellipticity interesting to us in the first place? It's because deformed triaxial rotating stars can emit continuous gravitational waves. This is unlike the waves produced by mergers and other things. So basically this is an exaggerated picture, but if you have a deformed star which is rotating such that its magnetic and rotational axes are misaligned, then that can be a source of of continuous gravitational waves. So what we now do is we have established a way in which the star can be deformed independent of the magnetic field just by virtue of the color superconductivity. So we look at the ATNF pulsar catalog, a famous catalog of pulsars, and we choose slow rotating and weakly magnetized sources such that the deformation from rotation and magnetic field are minimal, and any sort of deformation that could possibly arise could be from the color superconductivity. So in this subset of sources, if we impose the high ellipticities that we get from our superconductivity proposal, this is what we get. You can see that, for example, the instantaneous strain is not observable from any of these objects, but if we stack the signal, which we should do because this is a persistent signal, then over 1 year time, some of these sources do become observable. So these are various detectors. This is Advanced LIGO, Cosmic Explorer, Einstein Telescope, and this is the proposed INDIGO Indian Decihertz mission, which is called INDIGO. It's proposed. So the idea now is that, since magnetic field and rotation are low in these sources, any sort of deformation that is arising should be from another source, and we are proposing that it could be superconductivity. And you can see that some sources seem to be detectable, should have been detected by LIGO. So we say that the non-detection from advanced LIGO could be a way to constrain the extent of the quark core and or any structural effects that arise from color superconductivity. Of course, this is not a very strong statement because we are in a, we have various approximations and stuff, but this is a way forward to talk about the quark matter extent within neutron stars or hybrid stars. I want to just end on my last slide. This is basically prospects for future detectors, the Einstein telescope and the proposed Indian Decihertz mission, but basically the maximum distance up to which such a slow rotating source could be seen as a function of various ellipticities and frequencies. So if we do see any slow rotating, low magnetized sources within these respective radii, that gives us an idea that something could be at play in the star, and here we have proposed that it is color superconducting quark core. So I'll just end with my conclusions. The main takeaway is that pressure anisotropy in hybrid stars plays a key role in determining the structure, properties and observables. We have focused on two effects that could be sourcing anisotropy, that is magnetic field and a combination of color and proton superconductivity. I didn't go into details of proton superconductivity for want of time, but please look at our paper. And we have proposed two phenomenological profiles that could parameterize the anisotropy effects as they exist in the literature. We find that, this I had not shown, but it is often believed that in the very cores, it is showing up. It's believed that at the very cores of magnetars, superconductivity is absent because of the high fields can destroy it, but that's not true. Only proton superconductivity is destroyed, quark superconductivity can still persist. So don't worry about all the different panels, they are for different cases, but the green parts are basically for proton superconductivity and the blue parts are for color superconductivity. You can see that because of the high fields, indeed the green, proton superconductivity doesn't reach till the core, but inside the core you can still have color superconductivity. Color superconductivity requires much higher fields to be destroyed, so stars can still have superconductivity even while they are magnetar
fields. Okay, and yeah, an anisotropy can enhance the mass, overcome softening effects and leads to plausible mass gap candidates, and the enhanced deformation from color superconductive anisotropic stresses in one of our profiles can make the possibility of gravitational waves observable even from slow rotating weak magnetized neutron stars, and their detection or even non-detection could be a way to constrain the color superconducting quark core and its properties. Okay, thank you.
Very good. Thank you very much. One short question. One. We are running out of time. One, please.
Thanks for the nice talk. So did you look really at the stability of the very massive object?
Yes.
Did find this stability for quite axial shape?
Yeah. So I didn't go into the details, but yeah. First, the mass part. Okay, maybe I can. Okay, so the mass part is like we had considered 1D only. And then even in the gravitational wave part, we have just assumed that there is an angle of obliquity between the magnetic and rotational axis, and that is what causes the triaxial. So as I said, this is the ellipticity results. We cannot take it very quantitatively. We are just showing an estimate from 1D. It could be different if we consider the full multidimensional model.
Very good. Okay, so let's go. Let's run to next speaker, please.
Yeah, you know. One of these. Ah, there. The pointer. What's the pointer? Ah, here. Yeah. Because of this button. Yes. Okay. Great. Thank you. Thank you. Can you hear me? Okay. Great. Okay. All right. So I'd like to thank the organisers very much for this opportunity. So I'll be talking about the interaction of gravitational waves with matter. All right, and there are really two basic ideas that are behind what I'm talking about. The first is that it's well known that in electromagnetism, in a plasma, if the wavelength is below a certain critical level, there's minimal interaction, but if it's above it, they can interact significantly. And the question is, can one get the same for gravitational waves and matter? And the second issue really goes back to the foundation of gravitational waves. And originally they were predicted by Einstein in 1916, 1918, but it was 40 years later that it was realized, it was shown that they carry energy, and that was because of Feynman's presentation of the sticky bead experiment. After that, the theory of gravitational waves developed rapidly, and an important result is one due to Stephen Hawking in 1966, where he wrote down the formula for the damping of gravitational waves. This was in the context of a problem in cosmology. All right, so you just multiply by the exponent of minus 8 pi eta the viscosity and delta the distance through which the gravitational wave passes through the matter. Now, when you translate to SI units, you've got to put in a g over c cubed, which is about 10 to the minus 36. And there are no known situations where eta delta can be anywhere approaching 10 to the minus 36. So it's been assumed really since 1966 that gravitational waves pass transparently through matter. And what we did was reinvestigated that and shown that there are circumstances where that's not true. So the methodology used was the Bondi-Sachs formalism, where one can write down the metric in this form here. The coordinates that we're using, they're based on outgoing light cones. So labels the outgoing light cone. These AB are standard angular coordinates, say theta phi. And R is a surface area coordinate. So the area of any surface R equals constant is 4 pi R squared. All right, and we'll consider perturbations on a Minkowski background. So Minkowski background, we just put all these metric variables equal to 0. Okay, and then a perturbation, we use a standard separation of variables ANZ. So we've got a sinusoidal variation of time. These are certain types of spherical harmonic. The details I don't have time to go into, but they're closely related to the standard spherical harmonics. All right, and then we have these unknown functions, beta, W, U, and J of R. And the 2 means that we're looking at the spherical harmonic with L equals 2, M equals 2. The usual one where we consider most of the gravitational radiation to be. So when we put this separation of variables ansatz into the Einstein vacuum equations, we end up with equations for these unknowns, and we can solve them and obtain very simple solutions. So the solutions that we obtain are polynomials in 1 over R. So from a point of view of working with this is very simple. Okay, and we can also work out the gravitational wave strain at infinity, which ends up having this formula. For the time being, C40 is a constant of integration. We'll relate it to the energy given out by the gravitational waves a bit later. And in this gauge system we've constructed, this quantity J is just the gravitational wave strain, H plus IH cross. It's a complex quantity encoding the 2 polarization components of the gravitational wave. All right, so the next step is then we construct a model. So the model consists of a source, vacuum around the source, a thin shell of matter, vacuum outside the source. Okay, and the first problem we'll look at is dust. So there's no viscosity, there's just dust. Okay, and you have a solution to the equations outside the shell, within the shell itself, and inside the shell. You join the solutions together. You get quite a lot of constants to solve, but in the end, you do. I mean, this is actually, there's quite a lot goes into that, but I won't have time to explain that now. And what we end up with is a formula relating the mass of the shell and the radius of the shell. So H0 would be the gravitational wave strain when the mass of the shell is 0, and then H is how it's modified by the gravitation, by the presence of the shell. All right, so the first term is just the gravitational redshift. Okay, the second term would represent, it's out of phase with the leading term. So it will alter the phase of the gravitational wave, but not its magnitude. And the third term would introduce an echo. Okay, and then you get higher order terms as well. So when we did this work, which was a number of years ago, this first paper, there was an interest in there being echoes, even though it's now clear that, I mean, there was talk about GW150914 having an echo in it, but that's really been discredited now. Okay, but we can look at the magnitude of the echo term can be written like this. Now that term has got to be definitely less than 1, otherwise you've got a black hole and nothing's going to come out anyway. But what it's saying is that when the wavelength is long compared to the radius of the shell, you can get a significant effect. And this is pure dust. This is just an example. This isn't meant to be physics. What we've done is we've taken the signal from GW150914, which is the blue curve, and suppose that there's a matter shell of radius 900 kilometers and mass 60 solar masses around it. And how would the signal be changed? And what that shows is that it's not dramatic, but it's definitely, if you're talking about a nearby source, that's measurable. So it's not one of these tiny effects at all. It's not a 10 to the minus 36 effect or anything like that. That's of the order of a few percent. Now, where things get really interesting is when we start talking about viscosity. All right, so what we can do is we use the conservation equations to work out the velocity flow of the matter in the shell. And then we can construct the shear tensor of that velocity flow. And from that, the shear scalar, and then we can talk about the energy loss per unit volume is then minus 2 eta sigma squared. Well, it's still in geometric units. This quantity is evaluated, and it's actually quite complicated, but when we integrate it over a shell, and we also time average over a wave period, the whole thing collapses down, and we get a very simple formula out. And the formula that we get out is that the energy that is transferred into the matter is given by this formula here. All right, now the energy output of GWs is, we can relate this C40 squared to the energy output of the gravitational waves, and then write this formula as the energy being transferred into the matter in terms of the power output of the gravitational waves. All right, and then what we can do is write this, is that we must get this relationship here. We integrate that, and we can then end up with a formula for the gravitational wave damping. All right, and what we end up with is this, where alpha is the ratio between the outer radius and the inner radius of the shell. All right, so if Ri is much bigger than lambda, we recover Stephen Hawking's formula from 60 years ago. All right, so the only term that matters is the first one. But if it's the other way around, then we end up with something like this. And if alpha is, say, 2 or larger, and what we've got here is lambda over r to the 7. And if lambda over r can certainly be of the order of 10, 100. And then what we would get out of that is that that becomes a significantly large number. And all right, and then the corollary of if the gravitational waves are damped, then the matter will be heated, and they'll be heated according to this formula here. And what's interesting about that heating formula is this diagram here. The quadrupole formula, I mean, it's standard that the energy emitted at the poles is 8 times what is emitted at the equator. Right, and that's what we get for this curve, which represents the heating far from the system. But what we find is very close to the system, it goes totally the opposite way around, saying that the heating at the equator is going to be highly significant. And I just want to say, I mean, we've done it for L greater than 2, and the formulas exist. Now, on a general spherically symmetric background, we can also work out what happens. All right, but what happens when we go to general spherically symmetric is that the equations can't be integrated analytically anymore, and everything has to be done numerically. But what we find is that, in a way, the effect of moving from a Schwarzschild background to a from a Minkowski background to the more realistic Schwarzschild background, is that the damping heating effects increase by a factor of about 10 or more. So, I mean, that is something really significant. And what we've also done is to do this on a general spherically symmetric background, and what we find is not really quite similar to the Schwarzschild case. I mean, it's just the code exists and one can do it if one wants to. So astrophysical applications are going to be discussed in the next talk. Okay, they're there, but I'm just talking about the theory. And so what I'd like to say, the key point is that gravitational wave interactions with matter have long been regarded as being too small to be significant, but it may not be the case when the wavelength is much greater than the distance between the source and the matter. And I'd like to leave you with a list of references. Okay, thank you.
If no, let's move to last.
Yeah.
Any questions?
We can take that. I mean, that is one.
I just want to ask, if you only consider the mass of this shell, what's the role for the operation of this matter?
Okay. So all right. The first issue was we talked about a shell composed of dust, and then the equation of state is P equals 0. Okay. The second case we looked at was the matter being viscous. The equation of state actually turns out, when we looked at it in terms of, on a Minkowski background, it doesn't matter. On a Schwarzschild background, the pressure is obviously important, but it doesn't enter into the system. All that matters is the viscosity. Okay.
Thank you again.
Put it really close.
Okay. Like this.
Okay. So now we have a last speaker. This up to the section.
Is that fine? Yeah. Right. This thing working? No.
Screen.
Yeah. Oh, sorry.
Okay.
You can't use this one? Because yours is not working. It's not.
Don't use.
Do you have space to put that on? Oh. Okay. Cool. Thanks. Okay, thank you. Again, thank you to the organizers for the invitation to attend. So the talk is a follow-on from the previous talk. This is specific. We're going to talk about core collapse supernovae and expectations for the detection of gravitational waves originating from them. So this is work done with several collaborators mentioned there, and with the National Institute for Theoretical and Computational Sciences in South Africa. Okay, so it's not working after all. Let me just check. Let's see. Yeah, okay. So, like I said in the previous talk, the reason we can detect gravitational waves is they're expected only to interact very weakly with matter, if at all. So they can traverse large distances without interaction or without disturbance. But of course, this does not mean that they do not interact with matter. As Stephen Hawking mentioned in the 66 paper, that
for a perfect fluid, there's no mechanism for transfer of energy. So we don't expect any loss of energy for the gravitational waves there. But in the case for viscosity, there will be definite transfer of energy. Okay. So, as mentioned before, we use a thin shell analysis, and where this is particularly useful for the core collapse supernovae astrophysical case is that it models perfectly. When we look at the core collapse, when we look at the progenitor for the core collapse supernova in a few minutes. So, in terms of core collapse supernovae, as we know, they represent one of the most violent astrophysical processes in the universe. So, as the iron core of a massive star, let me just keep my eye on time. So as a core collapses, you expect, so as the iron core of the massive star exceeds the Chandrasekhar mass, you get electronic degeneracy pressure fails, triggering a gravitational collapse. So the collapse halts when the nuclear densities are reached, leading to the formation of a proto-neutron star and an outgoing shock wave. So the collapse, So the post-bounce hydrodynamics and anisotropic mass motions produce gravitational waves that are expected to be detected by current or planned observatories. So we in order for this to happen, the collapse has to be asymmetrical. Now, for now, most of the detection of supernovae has been through EM detection, and this is not ideal for understanding the physics of these stars because the photons originate superficially, so there's not much information carried from the inner regions of the star. So with gravitational waves, these are occurring deep within the core, and so this is going to carry quite a bit of information on the mechanism of explosion, and the fundamental forces that give rise to that. So, Now, the proto-neutron star would consist of a dense core surrounded by a less dense hot mantle, or the thin shell. So, hence our thin shell analysis, which we used for that. So, for some astrophysics of supernovae, we know that these occur for stars masses larger than 8 solar masses. Several stages of core burning is involved. I think most people know this from basics physics. As the shells explode outward, the lighter nuclear shells are forced outward, and so the next burning stage for the heavier shell takes place, and in turn each shell is forced outward. So what we have is a set of concentric shells, the lighter shells outermost, the hydrogen helium shells outermost, and CO shells closer to the core. And these continue until, of course, we know the final burning stage is iron burning. Once this is reached, there is no other balancing act for the star, and so we have a collapse of the core. So the nuclear fusion leaves the core inert. So the core of the radius has a density of iron dwarf with circumnuclear shells decreasing density away from the core with the relation given there. So typically for our N, it's about 1.5 to 3. So typically this is what we'll see for supernova with the famous onion skin layered concentric shells. So the supernovae collapse has been revised recently. It's from early expected processes, so there's been quite a lot of revision. Most of the models have to be developed numerically, and some of the earlier models were 2D models, which are inadequate to produce the symmetry we require. So now with current models, we have 3D hydrodynamic models, but these also are still expensive to run. So when we have the collapse of this core, we get two parts, an inner and an outer core. The inner core will, let me just see. So the inner core will halt collapse on reaching supernuclear densities when the nuclear matter stiffens. So this results in a bounce of the inner core, and you have a resulting shock wave launched into the collapsing outer core. So you have a collapsing outer core and a shock wave which reaches that collapsing outer core. So this bounce occurs very short time scales within 1 millisecond. And when you compare to, for instance, like binary black holes, there's a much shorter time scale. So there's a sharp burst of gravitational radiation. So with the gravitational wave signal we expect from the 3D simulations, this is not so much like a chirp, but more like a burst. Yeah. So the shock again loses energy to dissociation of ion nuclei. It stores about 150 Ks within 10 milliseconds of formation. The infalling shells of stellar material then pile onto the proto-neutron star, and these may drive the evolution of the PNS to B and H to a black hole. Yeah. So if there's a revival of the shock within a few hundred milliseconds, the resulting outward shock will lead to the expulsion of the infalling outer shells, leaving behind a stable neutron star. So there are two possibilities, either the black hole or the neutron star. Well, there are two possibilities amongst others, the black hole or a neutron star. So we also have, following the bounce, convection and the standing accretion shock instability, and these drive stochastic mass motions and asymmetric neutrino emissions. So again, we can expect gravitational waves, and these will be longer duration signals, well, longer in the sense of this activity of core collapse supernovae, lasting up to several hundred milliseconds. The frequency spectrum we're expecting to be about 100 hertz at early post-bounce phases, to about 1 to 1.5 kilohertz as the PNS contracts and oscillates in GNF mode. So there is also oscillation of the PNS. Okay, so just to summarize, the gravitational wave strain amplitude for core collapse supernovae at 10 kiloparsec. So the detectable frequencies, because the gravitational waves are so weak, is only galactic or galactic neighborhood, right? And so the statistical rate for that is galactic. Well, the last one was 1987, but it's predicted to be 1 in every 61 years, or say 2 every century. Sorry, the one in 1987 was in the Large Magellan LMC. The one that was galactic was, I think, 400 years ago, 1604, something like that. So we're overdue for one. So for the gravitational wave signals, the bounce signal is about 500 to 1000 hertz, duration 10 milliseconds. For the convection or SASI, it's about 100 to 300 hertz, lasting about 300 milliseconds. And for the PNS G mode oscillations, about 1 to 2 kilohertz. Okay, so with our catchment area, you can see that it's barely detectable with current detectors, but it is possible. So not with LIGO, but now with advanced LIGO, advanced Virgo. And then, of course, with the Einstein telescope and the CE, they should be well within range. So anytime now. So for our problem, I'm not going to go too much in the detail for the theory. This is covered already. We're using the Bondi-Sachs formalism, as explained earlier. We first used Minkowski spacetime and then extended that. We rescaled the gravitational wave strain, and we had a modified GW strain due to the matter shower. So in bringing these results to the core collapse supernovae, we see that Our GWs are generated by aspherical motions in the inner core, commencing just after the bounce. We treat the inner core as surrounded by an outer core, and we treat this as a thick matter shell. And although our analysis is thin matter shell, to extend to thick matter shell is simple matter, so to speak. We just simply treat the several thin, we simply integrate over the region, so we can treat it as several thin shells and integrate over the region. So let's see here. So for the astrophysical scenarios we investigated, which binary black holes, neutron star binary holes, or binary neutron stars, core collapse supernova, and primordial gravitational waves. For primordial gravitational waves, results were inconclusive. For binary black holes, the effect is negligible. For binary neutron stars, it's non-negligible. And for core collapse supernovae, it's significant. So we received the larger shell modifications for the gravitational waves for core collapse supernovae. And yeah, so the effects of matter shells are small in certain cases, but they're measurable if the signal to noise ratio is sufficiently high. So as hardware, 3 minutes? So as hardware developments pass, we expect this to be improved. So, is 3 minutes? Yeah, okay. So as I said before, with 3D hydrodynamic simulations for evolution of CCS, there have been some developments recent years, compare well for our inner radius for about, there seems to be agreement about 10,000 kilometers. Frequency seems to be in the range, again, of 100 to about 1,000 hertz. So let me just come to the results quickly. So when we looked at the gravitational wave strain, the frequency, the inner radius for the core, and viscosity, log of viscosity, we see, okay, we're plotting inner shell of the radius, on the x-axis, the gravitational wave frequency, and log of the viscosity. So what you see there is a surface with damping factor 0.5, so half. So for these values that indicated on the graph, this is where you have 0.5 or 50% damping. So obviously for above the surface, it'll be more or less complete damping, or increasing to complete damping, and below the damping decreases. So what you can see is that there is significant damping for realistic parameters. Looking at here, 10,000 kilometers, 100 hertz, and viscosity given there is 10 to the 15. So we expect damping at 50% for these. So as the yeah, it's rush. So as the parameters increase, the requirements for viscosity increase, so it's more unlikely. But what we can see is that we do expect damping, and we do expect it to be significant. So we extend the analysis over here to shell for viscous fluid, and as mentioned before, viscosity, we expect increased. Yeah, so we extended this to the viscous fluid, and we had taken our background to be a general non-vacuum static spherically symmetric space-time. So what we also get is we get heating of the fluid, and this in turn will produce further damping. So for these we had to use, so this cannot be done numerically, it had to be done, cannot be done analytically, it had to be done numerically. So it's found for the matter code, the damping and heating effects increase significantly, and it's possible for the GW signal to be completely damped. In this case, we can have GRBs, and that could be a detectable event that could signal to us that there's been occurrence of significant gravitational wave damping. So again, I'm not going to go through the equation, which has been done before. Just for a quick example, we took these parameters, realistic parameters, again based on most of the recent work, and so about 100 to 1000 hertz viscosity given there, total mass of 1 solar mass, and we find that for the matter code, the damping is even more significant. I mean, for the matter code than the Minkowski code in all cases, and we expect for damping. So this H1 is complete damping, and we can see that in most cases we're going to be reaching complete damping for the parameters that we're given. So for conclusions, we see that our analysis, we expect changes to both phase and magnitude for the gravitational waves. For Hawking's result is covered for wavelengths very much smaller than the radius. However, for wavelengths comparable or larger than the core radius, we found viscous damping has a significant effect. For the core collapse supernovae models, we find that in many cases viscous damping is highly predicted, so for now we expect, well, only at the high frequencies this should be detectable. So one of the consequences of this is that it significantly dampens our expectation of gravitational wave detections from core collapse supernovae. So not only are the events minimal, that even if there is an event, we expect that they should be damping based on our scenario. So as far as we know, this is a novel result. It has been accepted, which surprise hasn't been done before. So that's it. The code is freely available. Yeah, and I'm sure that it's on the website. Yeah.
Thank you very much. One short question. Any question? Short one.
You just passed very fast.
Yes, yes. Which one?
On the part of the binaries, can you please say again what you expect for the binaries?
Binary neutron star? Oh, for the binary black holes, the effect was insignificant, and the event is this. For the event, there's not much matter remaining anyway. So the same for the binary neutron star. So there isn't enough matter to constitute the tension.
It depends on the target that you put. But you have to put some target matter around or something.
That's true. Yeah, so you have to have maybe an accretion disk or some matter that's left around. And the other thing is that the matter has to be close in. So it has to be comparable to the wavelength. So you cannot have matter far out. So yeah, so that would be the problem with the binary neutron stars and especially with the binary black holes. Yeah, yeah.
Okay. I think all speakers are